Two more to go.
How are you?
Good to see you.
Yeah, this is Ray.
I'm Ray.
Oh, hey. Oh, yeah, I know your email address.
I know
just
yours.
Yeah.
No, I mean, I see a lot of patches. So good to put address, email address to face.
Yeah.
Nice to meet you.
Nice to meet you.
All the slides came through all right?
Yes.
Excellent.
We're loading them now.
Well, I'm going to rename this one for 09. I'm going to call it 25 improvement. Instead of LPC.
Yeah.
Oh, we didn't.
And then we just need to go here. And I just need to upload. And go to the
Okay.
and now I'm just going to test it. So when you want to switch, we just need to do. Okay, yeah. So, all right, perfect. Reports.
We don't, that's the difference. So we don't have any, we don't have any slides. We just
Oh, yeah. I edited the filler so I can accommodate.
yes, we should.
Yeah, give it.
We have more time.
Yeah. More control for it.
Good. Oh, yeah, thanks.
So we're done with that.
Yeah, you actually managed to get it done very quick. So this is the management. That's your management.
Yeah, I only
This one
had.
had,
I guess I'm not because this is like all the stuff that's so when they come up with that, we just need to tell them to
switch.
so that switch that and get the names or make it obvious. Critical.
You joined while I was Yeah, I know exactly. Yeah. Yeah, yeah. Hopefully mentioned rivals always. And right now also the PayPal stuff. And just by the way, Brendan.
Hey, nice to meet you in person. Yeah.
Yeah, I mean, you always. Yeah, yeah. Yeah, your blood pressure. So, the thing that we use, but there is now already as an approval, so you know, so yes, Google flag that's a couple of slides good at that, we know that. Yeah, I mean, I've only tried like once or twice, so we felt so long. So we so excited to go back into the yeah. Also, there's many kids. Yeah, I mean, really
Oh, right, that's right.
and also the doctor Jen.
We make things good.
Keep going.
So, where are these? I was gonna sit next to you and watch what you do. Because I have never shared with you before. I thought I
Yeah, the only thing is the first two letters. So, you know,
I'm sure you were.
I'm starting to like this Jeopardy roll better and better.
What was the last number you were at?
last year.
No, I was last one I had.
I think I talked to him.
Yes. Are you talking about the conference?
Yeah.
Sorry, I thought it was working. Okay. What's the car? Just yeah. Yeah. Yeah, yeah. It follows the. Yeah. Everything. People right here. Yeah. I think I was a little bit more worried about getting tried to break this one. Yeah. So, but it's okay. Yeah. Oh, right, yeah, you're dealing with the 9 hour time till the 3 hour time till that. Yeah,
We're gonna go fight. Yeah.
Well, I'm in Ohio, so that sounds great. David is based out of Australia.
Yes. Okay. Yeah, I thought, were you at the, were you at,
Hello, everybody. Hey, welcome to Kernel Dependability and Testing Microconference. So I am glad to see everybody here. We have several talks today. As you know, microconferences, we are going to be discussing and getting feedback from people. It's more of a discussion than a presentation. And with that, Sasha, anything to add? Okay. Sasha and I are just coordinating the conversations, and we want you to discuss and come up with a plan for where we want to take kernel dependability and testing to next year. All right. So with that, we have the first presentation coming up. Let's see if I can load the presentation. So do you see Philip in there yet? Yeah. I am not seeing Philip, so I'll just go to the next one. I don't see, yeah, I think I don't see. Mm-hmm. I put the slides up. So so should we go to the second? Oh, he did. Oh, okay. Okay, I'm messing up here. Okay. We have the first speaker, Philip. Is he? I don't see him on there. How do we? I don't see him. I put the slides up, but yeah. So do we just go to the second one? Who is this? Who is second? That's you. Okay. And come on up then. We'll go with you first, and then we'll figure out the next one. So the way you do this is you can pick your presentation from here.
Okay.
Just go ahead and then from the list. And then, yeah, go ahead.
Okay, and then you just advance with that.
Yeah, advance with that.
Okay.
And then you just speak to them.
Okay. Thank you. Okay. Hello, everyone. My name is Ray. I'm on the K-Unit team with Google. And I didn't expect to be the first speaker, but this is my presentation on storing and outputting test information. In particular, my project on K-Unit attributes, as well as KTAP v2. Let's see here. Okay, there we go. Okay, so this is an outline for my presentation. I'm first going to go over on a little bit of background on K-Unit, and then in general, what do I mean when I say test information? That's a very broad concept. Then I'm going to go further into K-Unit test attributes, and then how should we actually output that test information? Finally, I'm going to touch a little bit on KTAP v2, and then of course I'm going to have some time for questions. I also have a couple questions I want some feedback on, so let's get started. So what is K-Unit? So for those that don't know, KUnit is a unit testing framework for the Linux kernel. It's been upstream since 5.5, and the tests are written in C and run in kernel mode. We have Python tooling to run these tests and also parse the results. We have a really nice simple command here, just knit.py and then run. It uses UML or user mode Linux by default, or QEMU for any other architectures, and I've included an example here for x86-64. We also have the KUnit maintainer here, so he'll be giving a talk right after mine. Okay, so more on test information. So what do I mean when I say test information? First of all, I'm not talking about specifics during test execution, like what the variable x, what the value of that is at the beginning of a test. The definition I'm kind of going for is information primarily for the purpose of user interaction, either before or after the test execution. So an example would be like a test result or the speed of a test. Is this test slow or fast? The current norm for this test information is that we have the basics, so like the test result, the test name, and those are very well categorized, both in how they're stored and also how they're outputted. They're very clearly organized. And then everything else is, in my opinion, pretty unorganized. Everything else kind of falls into diagnostic data, or we may even have information like we know this one test is flaky or slow, but that information doesn't get marked anywhere and it just kind of goes missing. So my question is this a good system? Could we instead take that more interesting test information and make it more useful? So that sounds great, right? But the problem is there's still a wide variety of test information. I'm going to go through a couple examples to show what this test information is that I'm talking about, why it's useful, and what we would need to do in order to make it useful. So the first example I'm going to go over is speed. So the relative speed of a test. This is actually the inspiration for this whole project. There was a config for memcopy slow tests, and we thought this was really clever, a way to filter out slow tests. But is there a way to do that across the kernel, across KUnit tests? So clearly it would be useful because you'd be able to filter out these tests based off of how fast or slow the test is. But what are the needs in order to make it useful? We need a way to manually store that information, a way to filter based off of that information, and a way to output that into KTAP. And for those that don't know, KTAP is the kernel test output format. So it's the specification for kernel test results. The second example here is init. So whether the tests use init data or functions. Why is this useful? Because we could filter based off tests if it happens to be the case where the init section could be discarded, like in the case where we're rerunning tests. The needs for this, for us to make it useful, is a way to easily access that information and also a way to filter based off of it. Then I'm just going to go over one more example here. Output files is another example. So this would be a list of file paths of auxiliary files that are generated during test execution that could hold more context for the test results. Obviously, that would be incredibly useful for the test, whoever's running the tests. And the needs for that is a way to store that information during test execution and also a way to output that. Okay, so hopefully these three examples really demonstrate why this test information could be useful, but also it really begs the question of what can we do to make this test information useful? We need a way to store the information, both manually and a way where it's auto-generated, filter based off of the test results or test information, and then output in a readable and parsable way. Okay, so now I'm going to move on to KUnit attributes, which is a project I worked on and is now upstream. So the objective for KUnit attributes is basically to solve the problem I just mentioned. So a way to save and access that supplemental test information. We currently have two attributes. So we have the speed of the test and we have the module name. So whatever module is associated with the test suite. Okay, what can you do? You can create an attribute with pretty much any data type. So we use void pointers, so it's super flexible. And you can mark tests either manually, like with speed, or auto-generated, like with the module name. You can filter tests based off these results, and you can also output that into KTAP. But since KTAP is shared across the kernel, I'm going to go more into that later because that needs to be something that we agree and specify on. And then I've just included a small how to use this. You use this struct KUnit attributes And there's also a KUnit case slow, which would be specifically if you just want to quickly mark a test as slow. And then obviously you can filter based off of this using this module param KUnit.filter. And then we also have Python tooling flags that are the same, like according to filter or filter skip. Filter skip is just in the case where you'd want to skip the test rather than just completely not include it in the output. Yeah, okay, and then just to demonstrate why this could be useful, it's very useful even in my day-to-day. So here you just have KUnit run completely normal with the default settings, and it's 312 tests, and it takes about 10 seconds on my machine. But then if you filter out just 6 slow tests, it goes all the way down to 4 seconds. So that's 63% faster. And as you can see, it's really that running time, which makes sense, that makes it so much faster. It's actually 89% faster. So 7 seconds to about 1 second. So this makes a huge difference in just the speed of how fast I can test a large amount of KUnit tests. And then I wanted to include a list of potential KUnit attributes that I've been thinking about. First is init, which I mentioned earlier. We're interested in rerunning tests after boot, and in that instance, we want to be able to filter out all of the init tests. The second one is just the file path of the suite. That could be really useful for someone just during debugging purposes. The third one's kind of interesting, custom tags. So this is kind of more similar to how like JUnit would do their attributes. They have these tags. It's a list of strings, and then you can mark the test. And the good thing about it is that it could be very personalized. So I actually have a rough draft of this on my local computer setup, and then I can mark a test as flaky and then just run that one test case. And it's a lot faster. And then a final option is actually parameterized test attributes. So I'm looking to put an RFC out onto the list for this, but a way to implement a generate attributes function to assign attributes given a parameter. So I've even included like a little example here. If your eyesight's really good, you can see it. But it basically says if like the value of the parameter is 2, then mark this as slow. So it's an interesting extension for this project. Okay, but I told you I was going to go more into KTAP here. So all of these attributes are outputted into KTAP, but since it's shared across the kernel, if we want to change the KTAP specification at all, this needs to become a larger conversation. So what are the needs for the KUnit attributes and test information as a whole? We want a way for it to be identifiable, a way for it to be parsable. And because I think the most useful way to use this would be to have an actual specification in the KTAP spec, I've actually submitted this proposal to the KTAP v2, which is called KTAP metadata. It's a working title. But the KTAP line format would be this like hashtag type value. It's very similar to a diagnostic line for those who are familiar with KTAP. And that's on purpose because then it would aid any existing parsers who don't really want to pay attention to the KTAP metadata. They can just parse it out as a diagnostic line. You notice I've included this example here for suites. The KTAP metadata is in between the version line and the test plan. And then for normal test cases, it's just above the test case. These locations are important because they help the parser to identify what the KTAP metadata is. And also note that all the KTAP metadata blocks start with a header that includes the test name. And this actually solves another problem that we had as KUnit, where we wanted to include the test suite name before you do the results. So if it crashes halfway through, you can easily identify the test name. You don't need to get to the result line. But really, what metadata types should we have specified? And that's something I would love to get some feedback on. Things that are currently discussed on the list is, of course, the test name, the file path module name, speed, as mentioned before. Config info is an interesting one that we could consider, supplemental file paths. But yeah, what should we consider? And then I just want to note, it doesn't need to be a KUnit attribute. I think it's a bit confusing of a concept, so I included a Venn diagram here, basically showing that KUnit attributes and KTAP metadata can overlap, but don't necessarily need to be the same concept. And I've included a couple examples, like the test name would be maybe a KTAP metadata, but then not necessarily a KUnit attribute. And then a really interesting concept is that we could also have custom metadata types. because KTAP specification is a little bit slower, it would be really annoying if every time you need a new metadata type, you'd need to specify it. So we could use like prefixes to say that something is a custom metadata type, versus you could even use KTAP underscore for the specified metadata types. And that would even improve the parsability of this concept too. And then I just wanted to touch on KTAP v2 really quickly. So I've submitted this proposal, KTAP metadata, but I've also submitted a proposal for the skip test result. That's potentially a bit controversial, and we could talk about that more later. I don't know if it's necessarily pertinent for this presentation, but I also just want to mention that Frank Rowan has done a really great job with documenting all of the KTAP v2 information here at this website, and all the changes are going on in a separate branch within his tree. And yeah, I just wanted to open the floor to questions such as how should we continue to develop KTAP v2? What should the timeline be for all the future versions of KTAP? And yeah, so I wanted to open it up to questions. I have some leading questions here that I'd really like to get feedback on. I'll just read them through and then open the floor. But what KUnit attributes should we be saving? What is useful for people? Would generating KUnit attributes be helpful for parameterized tests? Is that something people are interested in? Are there specific attributes that if we do that, then would be very useful to include for parameterized tests? What are people's thoughts on this proposed KTAP metadata? What test information should be specified type of KTAP metadata versus a custom type? And then how in general can we support the development of KTAP v2? Yeah, that's my presentation. Oh, thank you. Oh, okay, toss it. Sorry.
Hey, it sounds weird to me that this is KUnit attributes, because I would think that the kernel's other testing infrastructure has similar needs. So like, how does self-test handle that? We also have slow self-tests. We have flaky self-tests. Why is it KUnit specific? Why is it not just like test attributes?
So the reason it's KUnit attributes is partly because of me. That's my background. I work on the KUnit team, and I would love to hear more about K-self-test. The idea with sort of KTAP metadata is a way to specify it across those kernel frameworks. So if we had this like basis of the KTAP metadata specified, then it'd be easy to like match it with other frameworks, testing frameworks. So that was the idea. But if we want to make a test attributes concept, that would be great as well. Yeah.
I mean, I think it's an easier path to upstream, right? If you're solving just one problem and ignoring the rest, it kind of forces the solution to remain unique to KTAP. But if you expand the scope to try and annotate tests in general in the kernel, because we have a bunch, like if you think even stuff like RCU torture, right? Could annotate that as very long test. Maybe it's worth considering stepping away from making it KUnit specific.
Yeah, that's true. David, did you want to?
Yeah, I think that it's difficult to say we want a attribute system for all different tests in the kernel when we don't already have a way of describing all tests in the kernel overall. The KUnit attribute stuff works, I think, pretty well as this is the KUnit implementation of whatever attribute system we're going to end up using. The KTAP stuff mentioned, KTAP metadata, is generic across all different kernel tests. That can easily be used. Just add the appropriate print statement to your test to output an attribute, output some metadata. The way of specifying attributes, just because tests are specified in different ways in different frameworks, is by necessity going to have some sort of, going to be specific to a particular framework in some way. I think the only way to make that identical across all frameworks would be to remove all distinctions between frameworks.
So yeah, the K self-test, the goals of these tests are different. So that is one thing that makes it harder. Probably, I would love to see a common infrastructure, but we have to also see how it will integrate with that particular framework. So that's probably where we will run into issues with how do we integrate that into the same into different frameworks. KTAP is common. K-self-test uses that as well. KUnit is a unit test framework primarily for us. So I would love to see it, but I do also see the complexity of having one single framework for all of those. Parameter tests, we do have some of those in K-self-test. KUnit, it looks like you're able to use that and specify that to all the tests. And the nature of K-self-tests happens to be that we do not have a consistent way of specifying parameterized tests.
Okay.
So,
yeah, I'm really looking for that, any feedback on K-self-tests, because I come from the KTAP background and KUnit background, but then it's difficult to identify. Like, I think just the practicality of how to also output the KTAP metadata will probably come into a big play of how that is formatted and outputted. So if we could just get more engagement on the proposal for the KTAP metadata, I think we could come to some sort of agreement for at least KTAP. And then since some K-self-tests use that, hopefully we'd get engagement from both frameworks. Yeah.
Yeah. Okay, so your custom tag idea is very interesting. We've been, when we first introduced KTAP, we knew we were leaving diagnostic lines as just free form, which is just creates anarchy, right?
Yeah.
But so if you could crack that nut, that would be great. But the problem, right, is we have this big distributed team and people just choose whatever they feel like applies to their. So you kind of need the equivalent of an internet naming authority, right? You need someone who can collect the tags and start to enforce them. So one of the things you need, I believe, is you're going to need a test that tests to make sure the metadata on the test is not out of sync with the spec or whatever. So you need to maybe be able to collect the attributes from a test even though you're not running the test. So that's one idea. So
with the KUnit attributes, we do have that functionality. You can collect the attributes before running the test. It outputs them into just like a KTAP output almost. But yeah, that's an interesting idea. That part of the reason I didn't introduce custom tags, because I do have a rough draft of it, is because I didn't want it to fall into anarchy immediately. So I wanted to do like the speed and module name, which are very regulated and also potentially like very understandable across the kernel. So yeah, but I like the custom tags as well. That would be great.
So I think this is really, really exciting. One of the reasons why I've never used KTAP is I found it too limiting. And because XFS tests use JUnit and it being XML, it's a lot more extensible. But more critically, it allowed me to annotate test runs. So not only do I have attributes on individual tests, I can attach to a test output. This is the kernel version. This is the version of the test that was being used. This is the kernel config that I'm using in some sort of high-level abstract way. This is the file system that I'm testing. And then one of the nice things about JUnit XML is I can actually combine multiple test runs into a single output file that will have, this is ext4 with a 4K block size. This is ext4 with a 1K block size. And I have like 12 different configs with several hundred tests in each config and all in one single file. So this is clearly not going to meet that, but have you thought about adding attributes about a test run, right? What kernel version is it? What version of tests are being used? What config is being used? And because I think that would be really, really helpful. And then the other thing is if there are tools to convert between KTAP and JUnit and KTAP. One of the other reasons why I really like XML is I can import that into various dashboards that use the XML framework. And so the more we can actually have interchange and maybe have a bit more, functionality equivalence, then maybe we can, sort of standardize by, transformations and not have people choosing one format over another just simply because they need certain features that only one particular format can provide them at the moment. So,
yeah, that's a really interesting idea. Both the test run attributes, I hadn't really considered that much. I was thinking that'd be more like the KTAP metadata, but I would be interested in thinking about that more because I know people do have interest in like config info being outputted into KTAP. Yeah, and then standardization by transformation is also really interesting concept. Yeah, that if we had this standardized enough, we could start using these transformations more, and then that would even like back that specification even further. Yeah, that's interesting. I'll think
and
about
I think
it.
that starts to solve like the problem that we see in CI, that we are generating different types of data and outputs in different CIs, but we have some things that specified at the kernel level, the test run level, that will make life easier for a lot of people, I think.
Okay, yeah.
About attributes that could be useful for tests. I'm thinking about, I don't know if this makes sense, but for me, looking how test results and regressions are being reported, and we'll talk about that later in the last talk. I wonder if it would be useful to specify the area where the test is, the test is testing. Like, for example, test could be part of the testing, part of the core features of the kernel, or it could be a driver test, or could be file system tests. Because right now I can see the results either by test suite or by test name or by whatever. But if I'm a developer, I might be interested in watching, keeping an eye on the results that might affect the work that I'm doing. And that could be a way of classifying the tests all across the board.
Like a test area attribute
right.
that you can like specify based off of. Interesting. Interesting. Okay, yeah.
Either subsystem or something that identifies a test area, and if you could filter on that, say, I want to test the file system today, I want to test networking, that'd be great.
Yeah.
It's like a tag system.
Okay, great.
Yeah. Try a little bit of that.
Is it?
Everyone use the microphone.
Oh, yes.
So we can continue this discussion in the hallways.
Yeah.
Thank you. This is great.
Thank
And
you.
then, next.
Yeah, next up is
David.
David.
Okay, thank you, Ray, for starting us off with that, and we'll continue a bit on the KUnit theme for the next 25 minutes or so, with the slightly interestingly named testing drivers with KUnit, which I picked because I wanted the second line rather than because it's a perfect description of what we'll be talking about. I am David, and I'm the KUnit maintainer. So let's get started. If this works, okay. The what is KUnit? This is exactly the same slide that Ray just showed you all. For the people who have just come into the room or are looking online, you probably already have a pretty good idea if you're looking up testing talks, but KUnit is still a unit testing framework for the Linux kernel since 5.5. Basically, you write tests in the kernel and they run. If you want to know more, either watch the previous talk or pause and Google it if you're watching a recording. And similarly, there are several features which we've added relatively recently or are relatively interesting. The ability to add sort of resources that automatically get cleaned up, which has existed for a while, but we've improved recently with the defer KUnit add action functions and similar. Parameterized testing lets you run the same test code with multiple sets of input data. We have the ability to redirect function calls, which I talked about here last year, and some nice tooling features to run tests on different architectures in QEMU and with different config options. There's a website with lists, there's documentation in the kernel. You can search for things. I won't spend too much time on that. What I want to talk about now is the fact that some code's easy to test and some code isn't. And as the title alluded to, spoilers, drivers are one of the difficult to test things. So what code is easy to test? Basically, it's library code. Stuff that is really self-contained. So things like data structures and algorithms, we've got good tests for the kernel linked list implementation. We've got tests for hashes and hash tables. There are tests for crypto algorithms. These are all pretty self-contained. You can spin up a linked list in a test. You can try adding things, removing things. You're not interacting with anything big and global that was going to cause problems. Similarly, helper functions. The example I like to use here is we've got quite a lot of tests for things that convert timestamps from one format to another. Most of the different file system tests we've got, the first thing anyone tests in a file system is, can you read the weird timestamp format that particular file system uses and convert it to a standard Unix timestamp? Equally, converting from Unix time to civil time is well tested. But these functions are very sort of self-contained as well. They take an input, they produce an output. They're not, they might read a little bit from global state, but they don't do very much. Don't fiddle around with anything deep in the kernel. Parsers can get a little bit more complicated, but as anyone who's tried any form of string manipulation or other sort of data file manipulation in C, it's something you really want to test. And again, it's taking an input and producing an output, a parsed form of this code for the most part. And basically what this is saying is anything which in the sort of computer science sense is a pure function or has no side effects is easy to test. You've got, you can just write something that takes a particular input, calls the function, checks the output as what is expected. That's much nicer than something that, takes some input, takes some random state from your machine, does something, mutates all of the other bits of machine state, and then you've got to go all the way through the kernel, first finding everything and then cleaning it up. And the other area which can help is code that has really explicit abstractions. If your code is very modular and you can pull different bits out and replace things with fake versions, that makes it a lot easier to test code. If it's layered, that can help. You've got a layer which is a sort of user layer. You've got a hardware layer underneath. If you can easily get in between those layers and inject things, that makes testing that code much easier, particularly from a unit test point of view. You can do big functionality tests that pull everything in, but if you want to test individual chunks of code, they really need to be sort of self-contained in some way, or at least the interfaces around them need to be really explicit. So if that's the best case, what's the worst case? And the bad news is a lot of the kernel is the answer. Basically global state in whatever form your global state is. And that's not just global variables, even though we do love global variables in the kernel, or static variables, which are like global variables, but you can't tell quite as easily. It's things like, anything, two systems which are coupled tightly together. Not having that strong interface in between them makes it very difficult to isolate just one of them to test. The other sort of secret bit of global state is hardware state is global state. If you tweak some hardware register, you can't exactly easily intercept that. That's going to stay there. It's not a separate piece of hardware just for the test. There's real hardware there. So you don't want in your unit tests to be prodding real hardware if you can avoid it. And particularly, I think some of the newer GPUs might have things where you can spin up, special test contexts or whatever. But for most hardware, you've got one register and you need it to be able to boot your kernel. You don't want to be playing around with it just for a test. The other pattern we have a lot of in the kernel are bigger global lists of things. If you want to create a device because you're testing a driver, you have to register it in a big global list of devices. File systems, there's big global lists of registered file systems and the like. This basically means anything that deals with a file system or a driver or that is by necessity dealing with that global state. And that's a bit of a pain. I don't think it's a pain we can totally get rid of, but it's one of those areas that sort of limits the ability to just, I want to grab a function and test this. And finally, there's a bunch of other just implicit global state that we don't think about. Memory allocations, we've got one global allocator everyone's using. So by necessity, if you're testing things, there are more side effects than you'd expect. So why do we care so much about global state in tests? And there are three reasons, basically. With a test, we really need to know what the starting state of something we're investigating is. You can't just, if you've got, for instance, a function that adds 1 to a number and you're testing that it does that successfully, you need to know what the number starts with so that you can check that the result is correct. We need to be able to mutate state without breaking everything. It's no good if we decide we're just going to test something that totally wipes all of the page tables, because the test's not going to complete, because once the test's over, you've got no access to the rest of the kernel. So it's very difficult to mutate state safely if you're working on a real system, which, in KUnit we are. It's running within the real kernel. And you need to make sure if you're modifying something within a test, some other part of the kernel's not also modifying that in the background because it needs to keep the system running. And this is a pain because none of those things are true in the kernel. We always are starting in weird unknown states with, either uninitialized memory or, other drivers have booted and there's already a big list of registered file systems that we now need to slot the new one we're testing into. Maybe the one we're testing is already registered and already reading files off it if we start a test after boot. We're mutating state all of the time. All of these other parts of the kernel are modifying things. The kernel's running, it's a real system. And we can't just, as much as we'd like to, decide we're going to put a big lock around everything and say, well, while test's running, nothing can change, because, if you did, you'd hit deadlocks immediately. You wouldn't be able to use the system while the test's running. It's a pain. And finally, tests fail all the time. As much as we like to imagine tests are perfect things, testing imperfect systems, tests are themselves very imperfect things. They can fail, they can leak memory, they can put things in a bad state and never restore them. And while good tests shouldn't, it's difficult to rely on things working. That's why, KUnit tests and most other tests now taint the kernel when they're run, because frankly, code that's supposed to put things in a weird state and then eventually fix it if the test succeeds correctly is not something you want running on your big production system. So it's a pretty nasty state of the world if you're testing something more complicated than everyone's favorite helper add 1 function. So what can we do as authors of tests? The first one, and the least pleasant, or perhaps the most pleasant, depending on how you think about it, is design your code or refactor your code with this in mind. Minimize global state, or at least keep global state somewhere where you can avoid it if you need to. If you can't get rid of global state, and you can't always, hardware is global state and a kernel would be pretty useless if it couldn't talk to hardware. Try wrapping it in something that you can then intercept from your test and replace with a fake. Make good use of pure functions where you can, it's generally considered good practice now to, if a function doesn't need to have side effects, not give it side effects. And while we don't always do this in the kernel, and while the definition of side effect, can be interesting in the kernel, if we can move these things to independent functions, that helps. With basically the goal of swapping fake clients and devices and processors and user memory contexts and that in, so that we can operate on fake safe things where we can, rather than having to operate on real state and clean it up and hope nothing else touches it in the meantime. And also when writing things, trying as best we can to have really clean API surfaces, even internally to a driver or subsystem. If your driver is made up of several logical bits, you're dealing with a complicated device that has several different components. Try to have clean API boundaries around that. Even if you don't decide you're very explicitly going to maintain those as a stable API, it's good to have these surfaces where you can reach in and sort of split things apart so they don't become so coupled together you can't test them in isolation. So this is all well and good. Please, everyone, do this when you write your next subsystem from scratch. It's a bit difficult to do so with an existing driver or that. It involves a lot of refactoring. Refactoring is unpleasant, particularly if you're doing it before you write the tests, so that it's easier to write the tests rather than afterwards so you can check that it works. And there can be cases where, splitting things apart, things were written together for a reason. There are advantages to coupling and global state in that. It makes things simpler. It can be more performant in some cases. This is not a be-all, end-all, always do this, but, keeping this in mind is useful. If you can't, there are progressively more and more hacky ways to sort of force the issue. The function redirection feature we've recently added, or static stub, as it's also called, basically lets us annotate a function saying we want to be able to replace this at runtime, and then within a test, replace calls for that function to a fake or test-specific equivalent. There are a few things using this now. I know the ext4 mballoc tests that have just landed do this. It's pretty basic under the hood. Basically, just inserts an if a test is running, return fake function else real function thing there. But it uses all sorts of things to make this performant and not as ugly as it sounds. This is pretty good. It's actually not a bad way of inserting these API surfaces in where it otherwise would be a little bit trickier to do so, particularly into existing code. But at the same time, it's not as ideal as working on a perfectly architected, theoretically perfect system. There are some things like you really don't want to be suddenly replacing all calls to kmalloc within your test. That's going to lead down a very unpleasant path for you if you try, as the tests themselves and the ability to redirect things call kmalloc. If you need to export functions somewhere deep in the call stack so that your test module can access them, that's unpleasant. Multi-threaded tests are something that exist but are not well supported at the moment. If people want to, really have something to cry about, we can talk about those later. But the KUnit framework really assumes your test lives in a single thread. And if you want to do something else, you've really got to work hard for it. The other thing devices and drivers. This is sort of the struct device and struct device driver. A lot of driver code really needs this struct device pointer, a registered device somewhere to work. And it's not really practical to say, okay, let's go to every single device and every single driver and split it into a part that doesn't need this and a part that does, and only test the part that doesn't. People have been testing devices, drivers with KUnit for a while, and the way we've all done it is basically by using root device register to create a root device, and because that's literally the easiest way to get a struct device, even if it's not sort of the right way to get a struct device. And it's worked well. People have done it. The tests will pass. But as we've expanded that, talking to Greg in particular, everyone's going, hang on, this is really wrong. This is not a root device in a hierarchy. This is just a fake device. Platform devices have also worked. I know DRM's had some success with this. But you still need a bus of some kind to attach it to, and my preferred way of pretending you're on an ancient ISA machine and attaching everything to the ISA bus is a great joke, but not a great production answer to the problem. So we need a way to do that. One possibility is KUnit integration into device tree. Stephen Boyd sent out some early patches on that, which work but have not yet landed, which involves having a magic Linux KUnit board that you use with device tree. We're working out how best to handle that with device tree overlays and the like. I think that's going to be a part of the solution going forward. But not everyone's using device tree for testing, particularly if you've got, x86 specific devices or that where device tree is not as common. The answer, and there's an old RFC out there, and there's going to be a new one as soon as I find the time to send it out, is struct KUnit device, which is basically a device structure that's KUnit specific. There is a KUnit specific bus it attaches to, and a bunch of helper functions that nicely clean these up when your test exits, whether it passes or fails. It also can magically spin up a driver if you need a driver attached that, again, is just a stub with the name of your test. So that's sort of the state of things. And we've got a few forward-looking possibilities, again, to help try to solve these that I'd be very curious to hear people's thoughts on. One is logic IOMEM, which, if you haven't heard of, is a feature used by the VirtIO PCI support in UML. It basically is a fake implementation of IO memory accesses, where accesses to IO mem are redirected to function calls. Something like this could be really useful for mocking out hardware at a low level, and would obviate the need for people in tests to have lots of write to my register functions that are then redirected. But it's very UML specific. And porting it to non-UML architectures sounds like it could be really interesting and tricky. If so, we need to actually work out when we're trying to talk to real hardware, when we're trying to talk to fake hardware, and we don't want to do this in a way that totally kills performance on real hardware. So is that interesting? Is it not? We're not yet sure. We haven't played with porting it to non-UML, but I know Brendan has played a little bit with putting helpers around that to make faking registers really easy in the past. It also breaks everyone's current fallback approach of pretend real memory is IO memory, just malloc something or that, and cast it to an IO mem pointer and look at what the result is after a function's being called, which doesn't work on UML, but does work on everything else. Another possibility is variable redirection or static data stubbing. This is just an extension to the redirect function calls to redirect a variable, where instead of accessing a variable directly through some horrific macros, you access a pointer to a variable, and that pointer's value depends on whether a test is running or not. We've tried it, but generally thus far, it's not seen sort of enough excitement and enough use. We really want to push it unless more people want it because it's ugly. But could be interesting. I know there was some people looking at this for testing, global process lists and the like.
Maybe we only have 10 minutes to go, so maybe call for questions, and if anyone wants to.
will do so. This is, I think, the last slide. So the other thing then is the user context / MM context. Basically, people want to be able to do copy to from user within a test. To do that, you need some sort of memory context. It's tricky to spin one of those up entirely within the kernel without, there actually being a real associated user space process. There have been some prototypes on this, but it could be an interesting topic to discuss if people are interested. Or something else. So let's have a discussion.
So one of the big problems, of course, is emulating hardware. So what about some dynamic connection to QEMU? So you're doing the emulation outside the kernel.
So I know there was someone looking at this with a bunch of QEMU patches. It wasn't, a KUnit based implementation, but I think there have been people playing with this in the past. It's difficult for us to totally integrate this into KUnit specifically because KUnit's very much an entirely in-kernel thing. We'd need some sort of back channel to do that, but it's, interesting and worth thinking about more.
Regarding the hardware testing angle, is there any consideration of partitioning hardware and having some things run tests and some things not? So for example, let's say you have a test case that is handled within a single logical CPU end to end. Could we reserve that logical CPU, run the test on it so it doesn't have side effects or minimal side effects to the rest of the system, but is actually running on real hardware?
I think such a thing could happen. You lose the advantage if the hardware is specific enough that fake hardware gives you of you don't actually need real hardware to test it. But, I think for some hardware, something like that could work. I don't think it's, going to work for every different piece of hardware. There are some things which there can only be one of, but,
Right.
GPU contexts, I think you can spin up as many as you like within a thing that might work. Again, if you can reserve a core and you've got something CPU specific, that might make sense. Threads actually are a good example there of something which we actually have a pretty good way of keeping, CPU context safe. So we can do a bit of that with CPUs, I think.
So how much has KUnit grown over the last year for test-wise? Like, you guys are always slowly incrementing.
It's a pretty steady linear growth. I'm afraid I didn't put the chart in the presentation, but we're at almost 1,000 tests upstream now, and it's growing mostly linearly.
What are your biggest subsystems growth in the last year?
DRM is probably the biggest subsystem growth. There's a really nice little spike in the graph where DRM first started picking up KUnit a lot. But we're also seeing 2 or 3 tests, starting to grow in a number of other subsystems. And that's, really one of the things we want to see is, lots of subsystems starting to use it rather than everything constrained to one. But yeah, I will call out DRM particularly as, not only are a lot of the new drivers using KUnit. There's some retrofitting into old drivers, and they've got some CI integration they're doing with KTAP parsers and the like.
Is there a way to see the test coverage of a specific file or subsystem?
So there is. There are a few different ways. There are several test coverage tools that work with the kernel, but you can also take advantage of UML and just use gcov with it. There's a horrifyingly broken way and a slightly less horrifyingly broken way. If you're using GCC, this is broken. If your version of GCC is newer than 6, which is sufficiently ancient that everyone's wincing. But you can use it if you've got the old compiler lying around. We've also just discovered it works fine with Clang, even with newer versions. So if you're building the kernel with LLVM, the gcov stuff just works. If you're building it with GCC, you'll hit some issues with constructors and changes in the GCC gcov implementation, which we've, alas, not yet been able to fix. But it's possible to do. You can look at coverage, get fancy HTML charts and the like.
Thank you, David. I think we'll switch to Philip now. Thanks.
Okay, thank you, everyone. And, do come up to me and chat about it afterwards. Thanks.
Philip, can you switch the slides and be able to speak? Let's do a test.
Yes. Yes. Can you hear me?
Can you take presenter?
Okay. Okay, just wait a moment. Let me.
Oh, yes.
Let me see.
Philip, can you switch the? Oh, we can't hear you, Philip.
Okay. Can you hear me?
No, we can't hear.
Can you hear me?
I seem to be talking. Let's see if he... Is your microphone on, Philip? Yeah, your microphone is on. Can you check your volume and such? Okay, we can't hear him. We're unable to hear him, though. No. Okay.
Hey, Philip, can you try selecting a different mic or reselecting your mic?
How is now?
No.
No. Is it okay now? Can you hear me?
Philip, you're audible on the call. I think the problem may be going to the room.
Hang on, we'll check.
Is it okay now? Is it okay?
You're audible on the call again. I don't know about the room, but
So can you hear me? Still not? Okay. Okay, but the room audience cannot hear me now. Okay.
I think that what we'll do is we'll try and figure this out over the break, and we'll keep moving forward on schedule. And so, presenter Filippo, we'll let's try and figure it out over the break, which is after this talk. Okay.
Okay. Okay.
This is mostly a discussion. There's only 2 slides, and it's been a problem that was bugging me for a while. And the recent case of a certain embargo fix that came out about a month ago and broke all my stuff for a whole 2 weeks kind of prompted an attempt to try and fix that. So the embargoed issue stuff, it was created relatively recently, like it's only about 3, 4, 5 years old, ever since Meltdown, Spectre, and all of that came out. But we've been seeing a constant flow of kind of embargoed fixes going into the kernel. Some of them are more public than others. And we've been seeing a too large amount of issues with the embargoed code that was done in upstream and breaking a bunch of systems. Yeah. Yes. Aggressively.
Okay. All right.
Sorry.
Okay.
Yeah, we skipped like one forward.
Okay. All
right. And so this creates a few problems. One of them is that the set of folks working on embargoed fixes is pretty small, which kind of breaks the kernels if a lot of people see the code and bugs are easy to find. It also sees limited testing. There is a concern that if we try and do more extensive testing with embargoed fixes, then we will risk the embargo itself. Someone might see us testing it. The fix might leak, and that will kind of make a mess of the embargo. It's also the case that embargoed fixes are relatively complex. They rarely just like check if something is null or return this error code. They're usually big refactorings of often the how we compile code. We often change complex assembly code. So like all the fixes themselves are something that would normally be reviewed upstream for weeks or months before being accepted. And it's also the case that there's no documentation. A lot of the fixes are, well, the CPU behaves in this way, and if we do this weird quirk, then it suddenly works. So let's just do it. So there's no way to verify that we're kind of doing the right thing with embargoed fixes. There were a few thoughts of what we can do here in the past. One of them is a dedicated tester group. The doc that we have in the kernel tree says that we can pull in people who are needed for testing code. But this wasn't done extensively in the past, or at least I'm not aware of a case where it was done even once. We also have, so usually these issues are within processors, and it's usually the case that there's other companies that can test code and have NDAs with a certain hardware vendor, and Ecodis is there. But there were similar concerns with testing. Like if we throw some code into like Microsoft or Google infrastructure and we run a big test on it, someone else might spot that something's going on and kind of try and sneak out and see what's being tested and then break the embargo. We've been thinking about setting up dedicated test infrastructure, and I heard from the Intel folks that they are trying to do something like that on the zero-day bot. I'm not sure what the extent there is, but as far as I'm aware of, there's nothing kind of dedicated to embargoed code. There was thinking we can use like a dedicated kernel CI lab or something like that, where we can populate with some machines and test it out. It's also the case that we don't know which test to run. There's no like one big kernel test. A lot of it is different test suites, different tests. A lot of it is tests that end users end up running, in their environments. Like a lot of the testing is, users or companies testing during release candidate stages and finding bugs and reporting them. And this is not something that works well with the embargoed model. And so this is where my slides end, and this is where I'm looking for opinions about how this can be improved. And I'll go after the talk is done, I'll go back to the recording and try and create notes out of it and post them to in case somebody discuss. If anyone wants to start with opinions, thoughts. Where's the mic? Oh.
Who wanted it?
So when you speak of tests, are you referring to tests that are going to test the fix that's come in, or tests that are there to make sure that we didn't break anything in trying to fix this hardware bug?
So both, really, right? Like we had a few breakages where we thought we fixed the actual problem that was being embargoed, and that wasn't true. We also had cases where we thought we fixed the embargo problem and we broke something else that wasn't supposed to break. We had cases where things worked, but there was a massive performance hit that wasn't supposed to be there, and we had to go back and re-engineer the problem. I would say all of the above.
Right. So my question is, where are the tests coming from? Are they coming from the hardware vendors? Are they coming from some other source?
So that's a great question. Right now, they're not coming from anyone. Ideally, they would come from the users who care about this. So like if we care about certain workloads working after the fixes, we could provide tests. This is similar in spirit to what kernel CI does, right? When you can kind of plug in your test and it will run it for you. But right now, we don't have that infrastructure to provide tests to be run for embargoed issues, right? That there's no way for me to say, hey, Intel, if you fix this issue, please run my tests here. That there's no connection like that. And even if we would do that, it would be a one-off, right? That would kind of do it for me, but what do other people do? We need a more systematic way of doing that, in my opinion.
I'm not that good at throwing. Oh.
Try it.
Yeah. Hi, Sasha. How much of this do you rely on distros to participate in doing your testing here? Because this is something exactly what distros, like I'm from Red Hat. This is kind of our bread and butter, and we're able to contain the embargoes inside. If we had a standardized testing infrastructure, like all the the discussions we had earlier with KUnit, KTAP, and all that stuff, if distros all standardize upon all that stuff and could run those tests on their particular hardware and somehow in a secure way communicate that up to upstream, would that be useful in any way?
So I thought some distros do it to some extent, right? Like Red Hat participates in some of the embargo development and tests some of the stuff. I think that the tricky part is that the amount of tests there isn't what we would want it to be, right? We want to run more real workloads, right? Like we can always run self-tests, we can always run KUnit, but we need to also find a way to run with like real end user workloads. It's also the case that we can't open it to all distros, right? So like a lot of the distros are a commercial company like Red Hat, which we can do, Red Hat SUSE, but Debian, for example, there's no way to give the Debian community an embargo fix and ask them to test it quietly, right? There's no such mechanism, and that's something that we saw like originally.
Is there a way to get like the Debian community saying if there was an embargo fix, these are the workloads they want, and then companies like Red Hat could run those workloads and help out in that direction?
Yeah, it doesn't even have to be like Red Hat, but like some mechanism in the community that would do that. I just don't think we have the structure right now that would allow that to happen. We don't have that dedicated tester organization person group that would take tests or collect the tests and run them on behalf of various customers. It also raises questions of who owns the test infrastructure, right? Let's say I have like 20 Google tests I want to run. I can't give you like the whole infrastructure, and I can't maintain it outside of my company. So it can't be like, we need to minimize the amount of entities in play here, I think, rather than trying to overload some.
I mean, at Red Hat, we do a lot of internal testing. We have a lot of infrastructure. Sometimes it's just, we do the best of what we can for what tests we should be running, but we also have that same opportunity because we're running on upstream, is to expand our test suite that maybe not be Red Hat specific or workloads that are not Red Hat specific, but we can maybe participate.
Yeah, and I think that this is something that will benefit Red Hat even outside of the embargo story, right? Like you want to run more tests before you release a distro. Yeah.
You do have the issue, though, at least, and I've watched a lot of these embargo fixes as they go through and patches are ready and these things. A lot of times the timeline, the fixes aren't done quickly enough that you've got ample time to test. And so, yeah, I mean, like we've got some great testing. We've got a QA team that can test all kinds of stuff. But if there's not time to run a full test suite, I mean, we don't have a week. Or if you do run it and you find something, all right, well, I go through and fix it. And that's, so I think we probably need access to, some sort of a lab that could actually run several tests in parallel and do that kind of testing, maybe in stages even. So here's a quick pass, and we know these things seem to be fairly good. And then we've got, some workloads that are going to take longer to test. And so you get various stages of feedback from it. But I mean, can we set that up somewhere in some sort of a thing where the machines are secure, and any user could contribute to or could submit a build to it and get some testing feedback.
Yeah, so I think you pointed out two things here. One is that there's not enough time for testing at the end, and I think that this is a more systematic issue because usually embargoes are actually pretty long, right? Like we saw embargoes of over a year, like we'll fix it in the middle of next year. So clearly there's time for testing there, but I think that we never budget time for testing. We like it has to be done like at the end of the year. Okay, so we'll finish the code on December 25, and then you can test for a day or two. And that's a separate problem. I mean, it's tied to this, and it's definitely something I agree with you. We should highlight and we should make it part of the process. Maybe making the statement that the mitigation has to be code complete a month before it goes out of embargo or something like that. The second one is actually, I'm not sure. I understand where you want to go, but I'm not sure how we can create that structure of like what is that safe environment for embargoed code. Like, where would the machines live? Who would own them? Is it the Linux Foundation? I mean, maybe that's, or is it Intel AMD? Maybe. And maintain them. Yeah.
So why not use kernel CI kind of infrastructure? Why not use existing ones? And you can, with kernel CI, you can go and add your tests if you like, and people can submit tests. Why not use that?
Yeah, so I definitely agree on reusing the kernel CI infrastructure. I don't think we need to reinvent something new here. My concern is around where, or like, how do we test and where are those machines hosted? Because we can't run embargoed code on kernel CI because everyone can see what they're pulling from. It will need to be kind of parallel, separate story using the kernel CI code, but separate infrastructure. But who will own that infrastructure and who will run that?
Somebody commented, Mark commented on Debian does have a security team, manages. We were talking about Debian earlier, so just wanted to point that out.
Yeah. For kernel CI hosting, that sounds like something that the Linux Foundation might be able to help with. I mean, kernel CI is a Linux Foundation project already, but yeah, it feels like something that it's shared infrastructure that everybody uses. So it does feel like a good fit for Linux Foundation.
It feels like between kernel CI and OpenSSF, both of them being Linux Foundation, we could find a middle ground there. I think that the concerns then become of the embargo itself and like NDA between parties, because kernel CI doesn't have a notion of NDAs, and I don't think OpenSSF has a notion of NDA. So we'll need to introduce, like, it becomes a difficult organizational structure to support, I fear.
An option
of
So you could have an option that when you're submitting a kernel to test, that there's a checkbox that essentially says this is private, and if you do that and you hide the data behind that, I mean, I think that would be enough. So nobody else can see your results, unfortunately. That sucks, but you can see them. You can share them with the team, with the people you're working with, or you can, depending upon, embargoes are different. It depends on the embargo. Something like Spectrum Meltdown, where companies weren't even allowed to talk to each other about it, even though they were read in, that's a problem. But for a typical embargo where there's a list, people can talk, and here's a link to my test results, or here's my test results. So you can actually send that out to the list and talk to those people. But when you submit it, as the submitter, you're the only one who can see the results.
Good.
Yeah. One thing about hardware access is we need to remember that it can't be a one and done kind of thing, because hardware evolves, right? One of the challenges with a lot of the currently existing test pools is, they were funded N years ago, and they may have equipment that might have been state of the art 5 years ago and is perfectly good for, running arbitrary, Power 5 tests, say, but won't necessarily be good if you actually need a fairly recent networking card or CPU, depending on where the embargoed code lives. And then the other thing to remember is some of the testing which you might need to do might actually require a fairly hefty machine, like being able to run a Postgres database. This is very, very different from a single board ARM motherboard that might be in a kernel CI infrastructure. So it's a very, very expansive sort of area, and that's going to be the challenge with trying to do centralized hardware, which is it gets expensive, and then someone needs to keep it up to date, because otherwise companies lose interest after the first year or two, and then we have older equipment, and then the problem hits again in a couple of years.
I would also say centralized hardware is no longer going to be a reality because some of the geopolitics around it. For instance, none of our boards are going to turn up set up in the US.
Good point.
I mean, could we have can we make a test suite that is embargoed itself that can be deployed? So, like, and it might have to develop lazily over the years. Like, we have a base set of tests, we run it, checks out, it gets publicly released, like the patches. Somebody else finds a bug with their use case. So then the next step would be, well, if you want to contribute, you can make your test case part of our embargo test suite that people can run.
I don't think it has to be an embargo test suite, right? Like right now, you can run, in theory, tests on an embargoed code with all the test suites you want. The question is how you do that. Like, I don't think that the tests themselves need to be secret. I think you're talking about, let's standardize a test suite we run for the embargoed issues.
Well, I mean, if there's certain users who have a very intellectual property sort of test environment or a use case, and they don't want their use case to be public, could we make their use case embargoed as part of the suite and say, we don't know, we're not going to expose your use case to all of your competitors, but at least we can run it, with a subset of, hardware vendors. Because I see that problem with, as come from a hardware company, you do as much testing as you can internally, and then your customers will find bugs because they have use cases that are unique to them, and they may or may not want to share that with you. And so it's sort of, you're in this weird sort of paradox.
Yeah, that's a difficult one, even without all the embargo stuff. Like, how do you test code? Well, possibly. It's probably just a further phase, though, of let's add more secret tests on top of what we can do, because right now I don't think we even run the open tests well.
So not an actual solution, because I think this would probably take you back around to the test groups thing. But I think we've kind of danced around the point of what if people were all running kernel CI? So at least, even if people have their own tests that maybe rely on some internal infrastructure, if the endpoint, like the interface for that test and the test results, all match the same format, then at least coordinating between the embargoed parties, maybe that would be a little bit more feasible.
So standardizing kernel CI as an API rather than
yeah.
I think that's a good idea. But also, I just don't understand the scale of the problem, because we're mostly talking about Spectre stuff, related fallout of Spectre, aren't we?
And others. It's been a constant flow for the past 3 years now, once a month.
Yes. Spectre-y things. The rest is not really embargoed. If you report something to security@kernel.org, they embargo it for a week. It's not a real embargo.
There's a lot of 90-day embargoes as well.
not that much on security at kernel.org.
But not on the on the hardware vulnerability stuff. There are pretty long embargo, and there's more than that. And they usually don't end up with security.
Yeah, exactly. But they're not like the majority of security bugs.
They're not the majority of security bugs. I think that the majority of security bugs are handled well. I'm thinking the ones, maybe I should have like explicitly said hardware embargo code. I think most security bugs are handled fairly well.
They also tend to be some of the nastiest to fix, right? Because you're really trying to work around problems in the hardware, and it's a workaround, it's a hack, and it ends up, yeah, you get performance problems out of it, you get all sorts of things because we weren't meant to run this way.
So a couple of things, right? One is test itself. We do not know what all the tests that use cases and tests that should be run, and containing that test environment so that we are not leaking the information. And there are multiple things. Some of them could be fixed with policy. Some of them are, how do you know what tests we need to run for that particular case? There's, I think it's some of the suggestions that came out, good suggestions. And I don't know that we can identify, us saying, hey, run KUnit or K-self-test, one of those will help. However, there is an unknown part of the tests or use cases that need to be run as well, as you're mentioning.
I don't think I fully understand what you said here, right? Because it's not a hardware bug. If it's a hardware bug, then the hardware, whoever it is that's going to fix the bug is going to give us a patch and a test that goes with the patch, right? That should be the norm. And then once we make sure the bug is fixed, then we want to make sure that the fix is not really having side effects in performance or something else, or perhaps breaking something else that we didn't expect it to break. And that's where we probably want to run as much of test collateral that we have to make sure that nothing that we didn't expect happened.
Yep.
So the first part is really the key thing, right? The new tests to be written, because obviously the old test may not catch the leakage or whatever it is we're trying to fix.
Yeah, so you need the new test to fix to test the specific of the thing that was fixed, but you also need to be able to run the rest of your test battery and see that nothing breaks.
Exactly.
And some of it may require, just given how complex the issues are, so some of the test failures manifest as like data corruption, that you don't notice on 2% of your machines, and you can't test that scenario out because you can't roll out that embargoed kernel to your fleet and test it out, right? Because it's supposedly needs to stay secret. And if you try and roll it out, someone might notice that you're testing an embargoed code. So you're blocked from testing of the more complex failure scenarios in this case. And this is what I'm trying to get to.
Is that even reasonable to address, in the sense that if I want to roll it out to 1 million machines to get the feedback from the entire fleet as part of the initial testing of the embargoed code, that probably is going to be difficult, right? So we do what we can, and then obviously we'll deal with issues that come out of large-scale deployments, as we normally do. Anything new that goes out to the fleet, we have safe deployment practices where we kind of slowly expand the radius, if you will, of the attack surface or whatever, the blast surface, really.
Yeah.
And then we roll it back if something bad happens.
If there is nothing else.
Any other questions?
So more of a comment to annoy people than a question, but one, if we're looking for lots of hardware to run embargoed tests due to a hardware issue, the vendor that had the issue seems like an obvious option as the person who should provide all of the hardware to test it on. If we had a standard kernel CI API thing saying, hey, look, unnamed hardware vendor, you've just told us you've got this really nasty issue with your CPUs. Can you now give us a fleet to run a whole bunch of tests on? Here's an API endpoint we can guarantee is embargoed to put results.
I think it's a fair point about who should provide the machines. I don't think it answers the question of where the machines hosted, who keeps them alive, and who keeps kind of refreshing the fleet with and keeping everything going. Like as it was pointed out, you can't put them in one data set or somewhere, right? It has to be also.
Yeah, but equally, you don't necessarily need to keep those around forever. Like if you're specifically testing one particular issue, you want. No.
So one of the common case where we've had testing trouble with embargoed fixes, it's not been the hardware that had the issue that wasn't tested. It's been splatter breaking other hardware. So, for example, we broke 32-bit EFI with one of the hardware fixes we had last year. And that was none of those platforms were affected by the issue that was being fixed.
That is a tricky one. The only other thing I'd quickly add is for people with weird or large workloads that they've not been able to test or they've want to keep secret. It would be very, very nice if we could get people who have these workloads that keep breaking when weird things happen to submit smaller, more sort of k-self-test, k-unit style tests that exercise the same thing in the cases where that's possible. It's not always possible, but it would be nice.
So yeah, we have about 3 minutes left. Any other questions?
So going back to everyone uses kernel CI as a common API. I know there was some discussion in the past about using like the official kernel CI as more of like a database that other people can contribute test results to. So if we had embargo participants who own their own hardware, who have a vested interest in solving this problem, make their machines available for testing, they could use kernel CI as a common place to send results. We might just need to have some kind of like embargoed view of the test results. I don't know. But using kernel CI as just an API for different instances to talk to each other sounds like something that might be interesting.
Mm-hmm.
I can comment from speaking with my hat on from a company that's very secretive. We're not going to put any hardware out there for people to test on, and we're not going to give you test results for hardware that's under development. So, I'm sorry, but that's
also fine. It just becomes
reality.
It becomes your company's problem. That's fine, right?
Right. That's fine. Well, it doesn't matter because we're on a 5.5 kernel anyway. So.
Thanks. All right, thanks everybody. I'll summarize what we've discussed and I'll send a mail in case somebody discuss once the recordings are up. And I think we'll have a 30-minute break.
Yeah, we have a. Could you put the break thing up?
Break
and then,
thing.
yeah, Philip will start with the. Apologize for the schedule change, which was needed to be done. And then we'll start with Philip's talk when we come back.
I put in the announcement that the schedule has changed. Announced sessions talk, so people should be aware.
Right. Thank you.
Yeah.
Nice to see you. Yes. Yes. Or that's right. I don't work. There are always going to be a number of different sorts of tests that you want to do with frameworks and some, but having a common interface to so you can say, run the I don't care
It's another day, man. I love days like this, though. Time flies. That's what I love about it. I'm gonna go in the other room and get the batteries. But we have a 15-minute break. I have my guys downstairs in Magnolia right now. Wanted to check and see if we can do anything. We like to wait till lunchtime.
You can check me on nothing affects. We're having the same thing in B, so it works there.
Okay, cool. All right, y'all know I'm here. You know I'm gonna text you. I know you're gonna text me, so let me know. I'm gonna change the batteries in this, and I'll change the batteries in the podium mic. So, and
the remote can stay in here.
oh yeah, because it's gonna yeah. Don't let me leave this right here. Good thing you said it. I'd have been in the hallway.
Yeah, I know. It's gonna be. Thank you.
Yeah, that's sort of
That's not
some of those quickly enough to make it go into setting up all these no tests are greater than possibly that there are people who respond to your testing. They do run CC and everything. There are a few things I think about LPC run all of the tests and do set that as a requirement. This is happening. It has to be with which is the right thing to do. I mean, there are some of the things that it's easy to sort of say, here's the statement, okay,
Pretty good. I just want to make sure the catch box is good. Did y'all need me batteries to work quick? Just let me know. I have 9 volt and I have check 1 2 2 2. Hey hey, check check. Check 1 2 2 2. Hey hey. Mic check 1 2 2 2. Check 1 2 2 2. Check 1 2. Check 1 2. Check check. 1 2 2 2 2. Check 1 2. Hey hey. Check 1 2. Check 1 2. Check 1 2 2 2. Everything pretty good?
Going well from your end. It looks like from other end.
The only thing that freaks me out is this.
Oh, are we throwing it?
No, it scares me. Like I'm not used to this. So this is
Oh, no,
the camera follows it.
What is that?
Yeah. So it has a tracker. Wherever it goes, this camera will follow. It is. It's cool, but I was like, oh, I'm not used to this.
We're showing it can work.
Yeah, nobody's. Is it on?
It's on.
I can turn it off and then we can start.
Well, we started today. We started next we are going to
Let's give it like while we work.
real sources. Yeah. Those of which are like, particularly for these smaller and forcing it to have these really big, ugly sentences which are rolling out to 1,000 machines that run our real world. To start writing those regression tests where, oh, my big ugly test works. Can I now write a small test that also capture much quicker earlier in the process? That's something I have written several documents saying it would be a good idea if people did this.
That's always been my trick with the community.
Not necessarily. I mean, we got as many people to try to put something up, but I think it's kind of from you're disseminating institutional knowledge to community. That's like part of how it managed. From Germany. I'm a friend.
So I was going to post something a couple weeks ago that you had first conversation. Very complicated.
Thought out is an optimistic way of putting it.
Yeah, I'm still very much interested in that
It's still definitely a lot icier than it was then. A lot of people
it's ties to something because I think
we got as involved more filling on.
Yeah.
I mean, that was
My time.
Now we can start to plug in file trick.
Yeah.
It's always these very, very kind of more indirect sense that this community does work and eventually I mean, like, if one of you is like, one guy who got it, right, you say, you're real happy.
That kind of now I'm managing
So that's yeah. Just because everyone's creating their own yeah, my dream is to get use this kernel, spreading data as soon as you go to GA, or as yeah, that's a good shiny. Yeah, yeah. So it's like you guys are kind of moving in a similar direction. Yeah, I'm trying. Well, maybe not the upstream portion, but you got the hardware you want to try to stabilize it. Probably stabilize it quicker. Yeah. Yeah, yeah. It's I don't know. I think we want to get that's the direction I'd like to take things, but I think we're not even all corral in going that direction. So, I think that is why. Or actually, when did you see? Yeah. We started around like 2000, 2001. Well, you got to roll out there. People always ask me questions. I think I might try to talk to you. Oh, yeah. And Yeah, well, yeah, you're dealing with a much more difficult situation. I mean, I would love to underplay a DBA case like because sneak the key I was I'd love to be able to speak to it. But I guess it's 6 months long.
Right now, my clock is the first slot is running. I think you know what's happening. Oh.
Yeah, we're not going we're the same age. We got enough volume. Yeah. So maybe more control than uses. I think as long as you're dealing with something that's complex, like even in the ideal kind of situation, there's always going to be some but that's an area where I know that you have major advantage because we don't have to disagree with something, right? Like we don't have a free version of our history that we can get to community and be like, hey, yeah, we do that.
Is the audio?
So we don't feel like it's actual or like this period actually just like finding it. A lot of issues like these are horrible. Yeah.
Okay, you're on. Get off this phone cord. How are we looking for? Okay, cool. Come on. There you go.
We see a lot of early issues that way. you're always building then you can and then you start flushing out stuff early. You need to have a vehicle to get exposed to the yeah, we feel the same.
Is he on the video or he's doing audio? Because if he was on video, we would have seen him by now.
Yeah, he's not on the video.
Should be on in 3, 2.
No. Okay. I don't necessarily want it on. Does he need to turn on his audio?
Yes.
Video, I mean, of course. Okay, he's on.
Yeah.
Okay.
And still don't hear him.
Yeah, we still can't hear you. I don't know what's going on.
Okay. It's his mic you.
That's sort of the angle we're going. Yeah, yeah. No, we are. Like, I think for us, one of the
Hello.
so it's really difficult to like even if you manage to run against like a convertible kernel, like how are you going to show because like format you need anything.
Hey, Philip, this is Tim.
You can talk better than that. Yeah.
Okay, can you say that again? Do you? Oh, Tim. Okay, we
Hi.
could hear Tim, but yeah.
You can hear me.
But what
Okay.
about Philip? Yeah, I can hear you, Tim. What about Philip? Philip, can you check audio on your end, like any microphone audio, microphone levels or anything?
Yeah, I can hear the
Tim,
room.
yeah.
And if you can
Yeah.
hear me, I think it probably.
Yeah, Tim, I can hear you, Tim.
Okay.
I can hear you, Tim. Yeah, Philip, I can't hear you still. I can see you talk, but I can't hear you. Can you check your audio settings, microphone settings, just in case?
Okay, I just came
Yeah,
in to do a quick test. I'll drop off now.
Can you hear me now?
Yeah, we can. Yeah.
Can you hear
I'll
me
say
now?
this. Yes, yes, we can hear you now.
Okay, good. Thank you.
Is there something on your end, Philip? Is a microphone or something? Or I just want to make sure.
Yeah, I just rejoined the session and reconnect the audio.
Oh,
I think
okay,
probably
cool.
some network issue. Yeah, still network issue. Yeah, apologize
Great.
for this.
Don't change anything. Don't change anything. We'll be with you
Yeah.
in 2
I'm
minutes.
very sorry. Yeah.
Of course, no worries.
Okay.
when you said, it made me think about that. Maybe what we need is like a standard that doesn't necessarily define or continue format but it's specified the field. Well, I mean, as long as there's a way to specify, you know, yeah, eventually we'll want to have some sort of standardized naming of what the various metadata are. But you can write Python scripts that can translate between metadata names as long as you know, oh, this is speaking the Q unit flavor metadata names. You know, this is speaking the XFS test flavor metadata names, whatever, right? It's just as long as you're supposed to specify, say, test run specific metadata, and a way of aggregating test runs together.
Hello, everybody. We'll get started with Philip's session. Go ahead, Philip.
Yeah, okay.
Hello, everybody. We'll get started.
Okay, so let me start. Yeah, thanks for attending the session. Yeah. Okay, this is Philip. This is Philip from Intel, who is the maintainer of 3D CI test service, and aka the kernel test robot. So the robot does both runtime and build testing. Today, I want to share some observations and ideas of the build side. I think the build issue found by static analysis tool could lead to runtime bug. Also, the build error impacts the bisectability of both build and the runtime side. That's the reason we are looking for a bug-free build on the main line. So talk is organized as 3 parts. How is the current status? And the practice is kernel test robot adopt to discover issues and prevent them entering the main line. Finally, to discuss the challenges and look for auth input that how different effort can collaborate to drive the bug free on the main line. So let's start for the first part. This is the quick simplified overview of the build test effort in the kernel community. From the bottom, the green box, there are test suites developed and maintained to test the kernel from various aspects, including compiling, static analysis, the coding style check, and other rules check. All these are considered as the build test in this talk. So it's about any test that doesn't need to execute the kernel. On top of that, tests are planned and executed by either a teamed CI or individuals, which run one or some of the suites regularly and report out the status. Most status are in the form of the overall test results, such as pass rate, critical issues, and some may also add bisect results for the detected issues. All these are to promise the quality of the kernel, which has its own life cycle and development flow. Testing can occur in any stage, though different CI may have different favors. In this talk, I will share some thinking about how to reduce the escape of issues that finally landing on the main line. Usually for a test effort to result in high quality, things like test cadence, frequency, the stage a test starts to involve in, coverage, turnaround time are all matter. So if we look at the coverage, it could be related to how many configures were tested. And it's also related to what kind of test tools suites were executed besides the normal compiling. The diagram here shows the rough statistics for the test tools used to discover issues. Currently, this is based on the commits within RC1 to RC6, and the commit is counted if it fixes an issue. So the tool and who detects the issue are gathered based on the change log of that commit. This is not 100% accurate. From the data, it shows nearly 1/3 are compiling related issues, and there's also improvements around the various checks. like check patch, kernel doc. For the static analysis side, smash, sparse, coccinelle, and coverage also play important roles. One perspective here is more fixes we found on the main line also means more issues are merged and exist in current main line. So if we look at the current status of remaining issues on x86 on the RC6 release, so the statistics runs on different configurations and only count for the unique and high confidence issue. The issues are accumulated, so we can see there's a jump for the number when we tested with all mode or yes configure. Later, the rand configure continues to add new ones from all corners. It's hard to tell whether all issues are detected. As more configures are added, more issues could be discovered. There's also diagrams about the detail category, so you can check it offline if you are interested. Both above slides show some build issues are escaped to the main line. It could be caused by different reasons. For example, not all patch in the mailing list is build tested comprehensively by CI. Or the issue is detected on immutable branch, which could be caused by the coverage is not enough, or the test is not in time before the commit is merged. Also, sometimes it could be the long tail problem that some issues will happen to be discovered by random configure in an unpredictable time. For 3D CI side, we have several goals regarding the build test. We want to discover more issues. We want to bisect the issue or to block the problems as early as possible. Finally, try to drive the closure of issues. I think all these goals are to be done through the collaboration with the kernel community. At kernel, at the board side, the first step is the build test. And also we have the bisection. And finally, if the issue is valid, so developer would help to resolve it. And actually, not all issues are needed to be bisected. As bisection is just one of the methods to find the cause, especially for build. It can be fixed by going through the current code base for most cases. But we still think it's possible that the original author may have more context or confidence to fix or find out some unintended bug. So we still prefer to go through the bisection, and we think bisection can be viewed as a kind of bug triage. And we can provide more information, like what is the first bad commit that introduced the issue to so to speed up the closure. We start the build test with the shift left testing. On one side, we continuously add new repos, and we try to improve the success rate of generating the testable branch for the mailing list patch. In order to test this large scale of branches, so we adopt the merge strategy to form a single merged branch to do build. Another side is to add appropriate coverage, such as more random configure and extra checks. Because we try to make sure these tests can take effect in the earlier stage, so to reduce the escaped issues. One challenge is the false positive detected by static analysis tools or sometimes the compiler. So the false positive could be some low confidence issue or less meaningful issues in the context of kernel. Thus, the important part for us is to be conservative, to have high quality reports. We try our best to mitigate the possible false positive. We have defined the rules for high confidence, low confidence, and ignorable issues. So we're doing this by analyzing the input and the change log. For the low confidence ones, it means it requires extra effort to do manual check. So we got a lot of support from the community, like Dan, like Julia, to filter out the meaningless reports. If the false positive problem can be well resolved, we think these tools could be more easily deployed in any validation effort. One more thing is, if the change log can clearly show or point to what the tool used, what the detailed error message is, this would bring extra values to the data analysis. As mentioned, we also have one important step, that is the bisection. We think in the whole process, things could go unexpectedly wrong, which actually have quite some opportunities for us to improve. Besides, we need to check whether the issue is high confidence. In order to have the valuable reports, the board considered a few more things, such as whether the issue is already resolved in the latest head of the branch, or whether it is resolved in the Linux next by the time bisection is done. So there are challenges that blocks the bisection to bisect effectively. Not to mention the build failure that hurts the bisectability. Even the bisection is correct from the perspective of detecting a change. The font commit could be not the one that we want. For example, it could be a makefile change, which is not the actual cause of the warning, but just expose the warning. So we pay more effort to smooth the bisection. We record the patterns of all these gaps, so we can use the pattern to identify the unreliable bisection in the future reports. Sometimes we may find a way to mitigate the bisect gap, so we could rerun the linked bisections. Basically we form a knowledge base, so we can run the bisect more smoothly. Here we got a lot of support and feedback from the tester, maintainers, and the developer. Meanwhile, we could also see there are some bad smells that indicate certain bisection is not effective. For example, like the makefile change or the directory of or other scripts directory change. All the commits, if located on these places, they are suspicious. So quite some of them can be mitigated by patching the kernel source in every run, so we can make sure the makefile and the scripts change are consistent across the bisection. No matter the change is adding new compiling option or it does some bug fixes. So overall, the goal for us is to bisect more accurately and find the real code change that leads to the warning or error. Of course, some cannot be simply mitigated. For example, existing error, which changed its pattern, or exposed by commit, which fixes some blocking errors. So for now, what we do is just to try to analyze the pattern and to prevent a similar commit reported. So we try to make sure the report we send out has most value. The table lists some examples for your reference. They actually are randomly picked to demonstrate different problems that blocks the bisections. Yeah, but I will not go through them in detail. The step is how we add the tests to make sure we can continuously drive the closure and avoid the regression. Basically, we have three sets. One is the core tests, that is the must run. The second is the auto-generated tests. And the last piece of tests is the regression testers suite, which we gathered from the historical files. it's all about how we prioritize these tests. I think currently we don't have a very intelligent solution. For example, we expect we can understand the test coverage of build testing so we can reduce the unnecessary build test. For example, when we generate a lot of random figures, probably some of them are duplicated regarding the effect of detecting issues. So there's pretty much to improve.
Philip?
Yeah.
I'm sorry.
Yeah.
Do you have? Would you like to get feedback from the people in the room?
Yes.
We have
Yeah.
about less than 5 minutes now left.
Oh, okay. Sorry, I didn't notice time. So session is only 20 minutes or 15 minutes.
Yes, yeah, it's about 20 minutes of presentation, 15 to 20 minutes, and then you get feedback. If you want to discuss something with.
Yeah. Okay. So let me just jump to the final 2 slides. So there are some ideas and proposals, so we can have some discussion based on that.
That'll be great. Thank you.
So we see the challenges are 3 parts: how the change code are testable, and what are the test coverage. So we can see for testable side, mostly the problem is the mailing patch failed to form the branch. And for the test coverage, the false positive as mentioned, and also the resource pressure. The other challenge is if we enlarge or we encourage different CI to test more, will this leads to duplicated test effort. Finally, is the bisection problem, how we can form a consistent bisecting process. Yeah. Actually, there are 2 slides that we think we can share some proposals. Yeah, but I can leave the time to the questions now.
Okay.
Thank you for this work. This is interesting. I have a question. You do a lot of bisection for building. What's been your experience for bisecting with testing? For us at Red Hat, it's been a struggle. Have you had more success bisecting failed tests?
Yeah. So do you refer to how is the bisection success rate, or you mean?
On your testing.
I didn't catch the last part. Yeah.
I understand how bisection works successfully for building, but what about bisection for testing? You got a lot of false positives, right?
Oh, yeah. Right now, yeah, for testing side, for the functionality, I think we relatively doing good. Yeah, but also it depends on the scope and what kind of tests we deployed. So there are some typical tests like kernel self tests, LTP, XF tests. Yeah, most of them are easy to bisect. But if we talk about the other kind, like the performance set, it brings a lot of challenge for us. Even we have some automatic mechanism to detect the instability, we also require people to do a manual check. So when we got a report, we usually doing certain analysis to confirm, yeah, it's a real one. So there are a lot of false positive, right? Yeah. And I think the talk for just add one thing. Here the talk try to analyze build is because build is relatively easy, and for the runtime it's actually quite complex. Yeah.
Okay, thank you.
Any other questions? Anything? Oh.
Yes, not exactly a question, just to mention, I'm from a Sysbot team, and bisecting the kernel is a real pain, because when you it's not that every revision builds. It's not that every revision can be booted when you build it with the instrumentation. And yes, if you run even if you have a reproducer, it's not guaranteed that it will really work when you go back to history. So there are, at least on our side, we tried a number of countermeasures to that, but of course it does not make the process 100% reliable, unfortunately. So it would be nice if there would be some maybe common approach, because I think it matters for everybody doing kernel development. Yeah, thank you.
Thank you, Philip.
Yeah, okay, thank you.
I think next up, do you know who next? Yeah, okay. So we have,
Back to regular.
yeah, we're going back to regular programming. So, okay.
Hello, everyone. Should I just start right away? So hi, my name is Nicholas, and I work for Collabora. Today I'm going to be talking a bit about the work I've been doing to improve the status in the kernel of detecting regressions in device probe specifically. So basically, the motivation is pretty clear. We have a lot of device probe regressions. Basically, there's a big, the issue here is that there's a lot of big impact in the platform functionality, right? Because basically, for example, like we have a lab with many Chromebooks, for example, and basically most of the platform is comprised of hardware blocks that are driven by drivers. So whenever you get a device probe, a regression that impacts device probe, then you basically sure to have some issue with it. Oops.
Okay. Hi again. So yeah, my name is Nicholas, and I'm going to talk about device probe regressions. The issue is that most of the platform is comprised of hardware blocks, right? And in the kernel, they'll be driven by drivers. So whenever you have a regression that impacts those, you're going to see some impact in the platform's functionality. They are still like very commonplace. So I've been doing some work in upstreaming some the support for some MediaTek-based Chromebooks. And I've seen a lot of this kind of regressions over time working on this. And there's also like this issue. The problem is that these issues aren't immediately detected because basically there's a lack of tests validating that all the devices in the platform are actually probing. This is really like the first step in verifying the whole platform functionality, is verifying that the devices in the platform are actually working before you even start running the functional tests. To try and address this, so maybe the naive approach would maybe to just start by reporting all the unprobed devices in the platform, but of course that doesn't work because not all devices need drivers. You might have like some virtual devices registered by the platform. Then you have, there's this function in the kernel called call driver probe, which is run to call the driver probe function for each device. It does log errors returned from probe, but there are a couple shortcomings there because, for one, it handles some error code specifically differently. So if the driver's probe returns enodev or enxio, that's considered like a probe rejection. So the driver doesn't actually handle that device. But I've seen some cases of those error codes being returned like on an error path of the driver probe. So it gets like difficult to try and discern exactly whether the probe is failing or not, is just rejecting the match. For the other errors, it's logged as warnings, so not even an error. So like maybe what I'm trying to get at here is that maybe it's still kind of unclear in the core kernel whether an error from a driver probe is actually an issue or not. So, but there's an underlying issue here, which is that just relying on error messages logged from this function doesn't help in case the device wasn't even instantiated in the first place, or if the driver is missing for that device, because then the driver probe will never even be called. So you don't get anything from that. So I wanted to just talk a bit about what I've worked so far on this, and also Laura, who is here attending remotely. And then I can open the floor for discussions and to get feedback. So to try and address these issues, we did also have a separate test called bootrr, which we were running at our labs to try and detect this kind of device probes. But one issue with that is that they were relying on some unstable APIs. So here, what we've done is, so we got recently a k-self-test merged upstream to verify the probe of devices based on device tree. So the idea is that for device tree based platforms, you already have this static list of devices on the platform, and you can just rely on that, and also to do some parsing of the kernel source to verify, to extract all the compatibles from the driver's match, so that you don't get false positives, right? You can just check for devices on the platform that should actually probe and check whether they are probing or not. So if Laura is here, she can talk a bit about the ACPI test as well.
I hope you can hear me. Can you hear me?
Yeah.
Oh, okay,
Yes.
Great. Yeah, just a couple of words on the ACPI catches. So we tried to follow the same approach that Nicholas just described for the ACPI platforms. So in the ACPI platforms, of course, you have a nice description of the hardware already available and mapped in SysFS as well. So that should make things a little bit easier if you're trying to understand which devices are probed correctly or not. From what I could see from my first tests, this should work well for all those ACPI enumerated devices. So the ones that have a hardware ID or compatible ID property in the ACPI table. But it might be trickier for all the devices that are on standard enumerable buses, so like PCI and USB buses, for example. So there's an RFC upstream. If any of you have if any of you is interested in giving us some feedback on that, it would be much appreciated. We're just trying to apply the same approach for device tree and ACPI-based platforms. And yeah, as I said, the tricky part is like just trying to get a description of what's on discoverable buses. So I'll give the word back to Nicholas for a description of the work that we've done so far on this.
Right. So we have these two tests, right? The one for device tree and also the one for ACPI, which Laura just talked about. But there's a limitation there that we're basically just with those two tests, we can only test the devices that are statically defined. So for devices on discoverable buses like USB or PCI, we really need a different approach. So right now I have an RFC series on the mailing list that proposing a way to test the devices under these discoverable buses. The big difference here is that you start needing to actually have a static definition of the devices on the platform, because you're not getting that for free from device tree or ACPI, right? So that's one requirement for that test, to have like a per platform file describing the devices that are under those discoverable buses, so that they can be checked for whether they did probe or not. And the aim here is, of course, to describe this in a hardware topology, like in a stable way, because if you're going to have to maintain this static definitions per platform, you really need to make them only rely on stable, like on the hardware topology, which is something stable across reboots. So yeah, that's the idea for what we have for this test right now on the mailing list. And with that, I would like to open up for questions or feedback.
So I'll ask a question.
Yeah.
So you are looking you can't really, some of the hot plug type devices, USB and such, you can't really have, are you proposing that have a definition for all of those, even for the ones discoverable devices?
Yeah, so what we would have is, for example, so I sent, as part of the series, I have like an example definition for a Chromebook that I have, and you would have something like a file listing, like, for example, in this device, it has like a camera connected through USB. So you would list like a test definition for like which USB host controller is used for that device, like in to map the hardware topology, so that you can verify that in the test. Like you would check one for one the devices and verify that they're the right devices there and it has probed, so that it works.
Still doesn't solve the problem of somebody just inserting a device, right? So is it a limited scope that
Right.
you're trying to address?
Right, sorry.
So how would you address that?
Right. So the aim here, it would really be like to internal devices, so not something like not
Externally.
yeah, like it would be catering to this use case of like, we just have this platform and we want to first things like verify that all the devices here probe, so that we can later verify that they're working correctly with all the specific use cases. But so yeah, for the most part, we can just rely on the device tree or the ACPI. But for the devices that are connected internally through a USB or a PCI bus, then we would rely on these test definitions to check for those devices as well.
I think for like one of these cases that we have is like it's a lab where we have a bunch of devices in there. And one option is also that those files specifying what we have connected, it's something we can maintain at the lab level. So if, for example, we connect like some USB device to a Chromebook, I can have that like as something that the lab is managing, and then we can do our own test with that. But maybe for something that end up like in the kernel tree, it's more generic. It doesn't include any of the external devices. But maybe the approach, maybe what we're trying to propose here is like, can we create something that's like good enough for have inside the kernel tree, but people can adapt to run their own like testing, like their own peripherals testing, for example.
Sorry, I missed the earlier part of the slides because I think we started too early. But looking at the slides, you said something about not all devices need drivers.
Right.
And that kind of contradicts with, at least with the limited understanding of what you're trying to achieve here. So for those kind of devices, what are you looking for? You just want the list of devices, or?
So the only thing that I meant there is that like if you simply look at the whole like sysfs tree in the kernel, like you just look at all the devices and you try and check whether all of them are bound to a driver or not, like that won't work because you have like virtual devices and such. But what we really care about is the actual like devices that represent actual hardware. That's what we were trying to test here. Like,
so I run into a similar problem for my own internal testing. We run latest kernel on Pixel 6. And the best option I've found out so far is I'll boot a stable build, what I consider a stable build, and do a find on sysfs to find all the driver folders. It'll just give me a list of devices that actually have a driver assigned to it. And then when I make some changes in reboot, I check if those files match. If the output of those command matches. Is it kind of what you're alluding to, but instead of like running it on a stable build, you just want to check it in?
Right. That's also a way to do it. Yeah, what we're trying to achieve here is to not like so basically what you're saying that you first boot into like a non-good kernel and then use that as a reference for other boots, right?
Right.
There are like some advantages with doing it the way we're doing. Like for the device tree part, for example, if you at a later point like update the device tree, maybe the support wasn't done completely from the start, and then you get a new node in the device tree that wasn't upstreamed yet before, but it is now. Testing the way we're testing, like just looking at the current device tree and checking from that, we get a new test for free. Like, and in that case, where you're doing like you're using a stable kernel as a reference, you have to like essentially do another. You have to regenerate your reference, right?
So in this case, you're asking to check in the list of devices into the kernel tree. Is that what you're proposing here?
Sorry, I didn't get.
Is your proposal to check in like a file with a list of devices into the kernel tree for a particular board? Is that what you're asking for, or?
So basically, for the device tree test, we don't need anything new. We and we already have that merged, right? We just rely on the device tree file and the device tree and the sysfs structure to check for the devices that are probed or not. What the thing that I'm currently proposing is to have a list of devices only for the discoverable buses, which would be USB or PCI, because those cannot be handled by the device tree, right?
So even for device trees, actually, there are some drivers which will just look up a node, and not necessarily even having a compatible string, and then they'll kind of initialize it.
Right.
So how do you plan on handling those?
So for those devices, so the test, it first parses the kernel source looking for compatibles that are inside a match structure in a driver. So those, if you have a driver that doesn't use the driver core, it only like manually looks for a compatible in the device tree. Essentially, that won't be tested in the current test. Like it would just be ignored. The good thing is that it also won't cause any false positives. It just won't be tested for with the current test.
So I work in the x86 space on servers, so I'm interested in the discoverable part.
do you already have an idea of how you would plan to describe the system? And how can we vary it? Like, for example, I might have a platform that it is not a fixed platform, right? A server platform, let's say we have a 2P platform. I can either boot 1P or 2P. I can take the PCI Express, links and divide them up. So, I might have a BIOS option that says boot with like 1 or 2 slots at full speed, or boot with 4 slots at half speed, etc. And that's configurable based on user, preference. So, is this something that you're asking, like, can we take those into account and describe, and make some sort of like schema or something that we can easily apply? So in the lab we can test all the configs very minimally. Do you have some?
Yeah, for sure. That's something that I really like to get more input on, because as in my RFC, I only handled device tree based platforms, which is like the simplest case, where you just have like the controller for USB or PCI. You have it just memory mapped IO, and so like it's easier to describe the topology of the hardware in that way. So for x86, I've only recently started looking into how we could achieve the same for that, but I'm still I haven't figured out the details on that yet. So that's why like input from people like you, like which work on that, would be helpful.
Yeah, I mean, could you give an example of just your ideas in your head? Like, is it like some sort of like file that we can describe and we can extend that, or are you still looking for even that level of feedback? You know what I mean?
Yeah. So yeah, like I'm thinking of a file that we could basically keep as part of the test folder for each platform, and the as for the feedback, maybe like help with coming up with ideas on how to describe the hardware topology mainly for x86 platforms, which is what I haven't had much exposure to. How we could come up with a way to describe the hardware topology in a stable way for those platforms.
Questions.
Yes.
Really well. First, I strongly support the idea of doing something that encodes the information about the buses or the devices, because right now this stuff is encoded in shell scripts, right? Which is very ad hoc, or even worse, it's encoded in like GitLab test node scripts or something. But I guess my question is, what was my question? Now I lost my train of thought. Oh yeah, I'll give it to someone else as a question, and it'll come back to me immediately.
Well, back to like, how do we get started describing the topology? I mean, there's some libraries and tools that you can list out the hardware topology, right, and dump it to like XML file. Is there a paradox here, like that's depending on us discovering them, and so we can't use that, or can we use that to help feedback into the testing?
Sadly, we ran out of time. Gonna spoil. So thank you very much.
Thank you.
No, you're not out of time. Yeah,
Oh, no.
the next session starts at 12:45. Yeah, you started this too early. You guys are just kind of off on your timing. Yeah. You are.
Keep going. Yeah, let's not start this while we check what's going on. Did what?
Tangential point. There's some other talk at LPC where they're like, oh, we need to describe the dependency between device and a PCI bus. There's some other resource in DT. So they're trying to figure out how do we kind of even have the kernel know that these things are there and they depend on each other. So for example, like a PCI device needs a USB or a clock that's defined in DT. So maybe whatever solution they come up with might solve your problem. So you might want to kind of take a look at that.
Oh, that's interesting to know. Thank you.
That sounds like something that at least is possible today with USB. I know that in USB there are ways to put in the device tree that says, hey, match this when a given USB device probes, and then it will actually add extra DT information from it. So presumably something similar technique. I think SDIO can also do that. So, okay, yeah. I mean, I can point them at you if you need, but sure, okay, sure.
Sure. Right. Thank you. Yeah.
All right. So in the PCI space, I might just recommend, first of all, this is cool. I like this. This is a great thing to have. I might also recommend that you make an effort to figure out if you can track like firmware versions on some of the PCI devices, because that is where you will have the most problems. Because everybody's updating firmware all the time, or nobody's updating firmware ever. One of the two. And you'll want to be able to know, because you'll have a case where one firmware works great with the existing driver, another firmware doesn't. People tend to avoid that, but you just never know what you see in the real world. So might want to add that to, unfortunately, add that to your test metrics.
So to the firmware points, when you say firmware, are you implying like in the device itself?
Correct.
Yeah, so at least in the x86 space, you can have your BIOS reconfigure the PCI topology and all that. So you don't just want to track the firmware of each individual device, but the firmware that's like global in the system. You might get a BIOS update that suddenly it doesn't describe, the topology, or it has conflicts in resources of memory. So that would be helpful too. Yeah.
That's good to know. Thank you.
This is not my question because I still can't remember it, but I guess just JSON. I mean, you didn't describe what your text format was, but I think your other question was like what types of things need to be described. At a high level, like if you just want to verify that like a web camera is present, just run the k-self test or whatever the test is that it's there. But I guess I'm trying to figure out what's different about the probe. Is the probe just to verify that it's there? Or I mean, at what level are you trying to test, right? So at the level of, is the device present, you can run any kind of test as long as it's at the right place on the right bus, right? But
what do you mean by that? Like, so the idea is to verify that device is there and it has been successfully bound to a driver, because, well, things might happen at any of those levels, right? For like one interesting case is like there was at some point a change in a kconfig, and all of a sudden the def config for ARM64 no longer enabled a driver that was required for some Rockchip platform, and then it basically broke the platform. So this way of testing, we're using the device tree and we'll have like a node for that device, and we can check whether the device has been instantiated from device tree, but also that it has been bound to a driver, which might not be true if like the kconfig is missing altogether in this example.
Okay, so you're actually testing elements of the device instantiation, not just whether it's present or not.
Yeah, like
so
basically the whole
adding
stack.
in some like diagnostics so that your test is more fine-grained on the results. It failed because of this instead of just it's not there.
Oh no, yeah, we're really like testing from the top. So we're looking whether like the test. The idea is that like if the test has passed, then we're confident that the device, like all of the driver core worked for that device, like it has been instantiated, and it has been matched to a good driver, and the driver has returned probe successfully because like and done all the steps that it needed to initiate the device. So
also, if I can add something, like these tests are, we thought about this as a baseline. So if you think of these tests integrated in a CI, maybe you don't want to necessarily have case of test built just to check functionality. So if once these tests are integrated in a CI and you want to have dependency, you can use this kind of tests as a basic baseline, like things are configured correctly and there's some kind of basic functionality going on. And if this test pass, then you enable those kind of case-of tests or key unit tests or more advanced stuff on top. But this should serve as a baseline in CIs.
So I'm still not clear on where you want this kind of representation to be stored. Does it reside with the test itself as a metadata? It's not very clear to me yet.
Right. That's what I was thinking about. So in the RFC, I have a patch adding the test, and inside the test folder, we can have like a folder, subfolder that will be matched based on like either device tree compatible or DMI for x86 platforms. And then you have like the list of devices to check for under discoverable buses for each platform.
So the basic problem here, right, is that different boards are going to have different devices. And so you can't, if you put something upstream, right, then you have this hard-coded list. So the best you can do, I think, is provide the template for that people can slot devices into for their individual products or whatever. So which is a good thing. If there's a standard way to do that, then automated testing things can use that, but it still has to be customized on a per product basis, right? So you can't put something upstream that if like a Raspberry Pi, then what are the BeagleBone people going to do? Unless you plan on having a catalog upstream of all the different boards in the world, which seems unreasonable.
Well, yeah, so that's one thing that I would like to discuss, because I think it would be good for everyone if we did have like that catalog upstream for all the boards. So like the same way we have device tree for every platform, like we might have one file per platform describing what is connected through those buses and like what we would like to test. Then different CI systems can rely on that instead of reinventing the wheel every time.
So that would be nice to have, like for the common boards, it would be nice to say, okay, is all the hardware on my BeagleBone work? Is all the hardware on my Raspberry Pi work? But in embedded development, your product's going to be, you're going to have a board specific file, and I wouldn't expect that to be upstream. So my recommendation would be to have, it's fine to put something up there as a sample, but make sure that it's something that people recognize and can easily modify for their own boards or their own situation. And maybe start there, because you're not going to start with a fully populated catalog.
One thing, as I've been listening to this and I've been hearing, since you're so focused on regression testing, I actually wonder if the right answer is to write scripts that connect to a board on one version of the kernel and then can grab out all of the stuff that's there and then use that to populate your catalog. And so then for the next version, you run a different version of the kernel and see if the list of hardware changed, right? And so it's sort of the database looks the same, but how the thing gets populated, anyone could run the script that could go populate it. And then if it's discoverable buses, they would also be populated. And maybe even you would then have it on a per board, not even a per device. Because even when you have the same nominal, like you might have, a certain Chromebook or whatever, and it looks the same to an end user, it may have different hardware on it, right? And so it's hard to check in that one static thing. And it would be interesting if you could just discover it and then catalog it. Anyway.
Yeah, I would say that is, I don't see us ever accepting the files for each platform. And think about in the long run, it would be very difficult to maintain and keep them current or keep them accurate. So that's not going to happen. So I would say something like what you're doing, And then what they were suggesting that having a script that would go generate it and use that, and that could potentially be associated as a test that would test this, could accept a metadata file to go test. It's a parameterized test that would accept a file, and then you would.
To play the devil's advocate to my own point, his comment saying, hey, we already have DT files, right? So maybe at least for the upstream boards, and maybe just limited to discoverable stuff, which is not clearly captured in ACP or DT. If it's possible to maintain a DT, why can't you maintain this too? Seems like a fair request.
Well, you're talking to the maintainer, though. Yeah, I know. Sure, that's what I'm asking.
Well, DT is, so you could derive it from, another way to do it is you already have a DT file. What can you derive from it? I mean, so DT file is necessary to boot a kernel, boot the platform. So what can you do with already existing DT file?
Yeah, I think for platforms that are using device tree anyway, if you could have some form of extension overlay for device tree and make that your format, for device tree based things, you've already got an obvious, well, if it's there's an upstream device tree and this is relevant to all things based on that, include that there. If not, you can have it as, per board overlays stored in the kernel if it makes sense. More likely, my suspicion is, as mentioned, the kernel tree is perhaps not the right spot for this. Certainly for, you don't necessarily want files in the kernel for every single variant of every single laptop ever made. But what particularly since the kernel tree evolves with the kernel, and if you're looking at regression testing, you sort of want these to be static things that are independent of the kernel's history. You don't want to bisect and then be dealing with old versions of these descriptions.
Even device tree isn't always believable. I mean, and so I'm saying that there's recent patches I've been involved with upstream where if you go look, for instance, the ThinkPad X13 has 2 touchscreens listed under it. Both of them mark status okay. Only one of them will show up at runtime because that's just the way it is, right? It's second source hardware. And so we're talking about ways to make that better, but the ways that we're making it better are going to be doing more probing, and it will, even for things that today may be discoverable just by looking at the device tree, may end up being more runtime probed. So even device tree won't give you a perfect answer.
Any other questions for Nicholas? I hope we got some good feedback to go back to work on. And
yeah, for sure. Thank you all so much.
So yeah, we are going to do the next talk. It's on the regressions topic. But if we take a step back and start where Nicholas left us, like what we've been wondering lately in our work into CI and testing at Collabora is like we are running a lot of like things on different CI systems, and we are taking a lot of data out of that. And there's like millions of tests or a few thousands of different tests that we are running every day. But are we able to analyze all those tests? Are we able to really like make sense out of it? Are maintainers happy with it? I don't think so. Like yeah. And then you start like thinking about it. Okay, what we should do? Maybe we should look into how we are reporting the regressions that we are finding. But maybe you should take a step back and look into the quality of the tests. And that's like where his work comes from. Like that we are looking instead of just seeing like a shell at the end of the boot process and say, oh, that's nice, it's booted. When it works, it's nice. You don't need to do anything. But when it fails, where is it failing? Like, which device failed? Like, we don't have enough person power, like to do this kind of work, like across the community. So we start like digging into different parts and to look into the quality of the testing that we are doing across the kernel. Like, I think what we did so far was maybe 2 months of work, but it's a beginning of like a process that we want to look at. Like, what's the quality of the test for the use case that we're interested in this case, that like the use case that Collabros clients are supporting us to do. And then moving forward, like running that in CI systems, improving CI systems, like we've been spending a lot of time on kernel CI. And then out of that, we go to like KCIDB, throwing all that data in there, and then we can analyze it, and we can like create like patterns or intelligence that will enable us to report better regressions to the community. So that's like the whole like path, like the whole like process that we're trying to ask questions, sometimes in a naive way. Oh, can we go back and see if we can improve device probe, or like can we look again into how we're reporting regressions, and try to ask like more simple questions, and sometimes in a more naive way, but we are trying to do something there. And yeah, let's get started. We're gonna take this part and then we keep like switching.
Okay, so yeah, so keep in mind that we are focusing on the regression side of things, because we believe that we have enough tools on the lower level part of the equation. We have a lot of data to work with, but ultimately the purpose of all CI systems is to detect regressions. And then the problem is what we do with the regressions that the CI systems are detecting. And that's where we are finding some gaps that we are trying to fill in somehow. So the current situation, as we see it, is that we have a few kernel-specific CI systems working right now, which do all the hard work of building up the infrastructure for tests. We have, well, there are labs with lots of different hardware, and there are tests running, and we are getting results. So we have kernel CI, CKI, zero-day, sysbot, bunch of things, and we are getting tons of data from the test results. But all of these are kind of storing the results in their own ways, differently, reporting them differently as well. There is a common place where the results are getting collected, which is KCIDB. That's at least trying to mitigate this problem by collecting the data from all these different CI systems into the same place. And there's also some effort to do some work that's not being a really big thing until now, which is keeping track of regressions, since they are all reported differently and they are getting worked in different ways from people all over the place. There must be some way to keep track of the activity, what's going on, who's working on what. So RegsBot by Thorsten, who will be with us presenting in the BOF on Wednesday, tries to tackle that problem. But there are quite a few problems, and just remember that we are seeing this from a naive point of view, from someone who just joined the party and took a look at what's going on. So I understand we might be opening a messy can of worms here, so we expect some fighting. But what we are looking is that from a usability point of view, there are a lot of developers who maybe they are not aware of the regressions that could be important to them. And on the other hand, there are some maintainers who are getting flooded with regression reports, way too many of them, and they might not be interested in all of them. That's because right now there's no really way of subscribing to certain parts or certain regressions. You can either get all of them or none of them, and you have to go to find them individually in different mailing lists. So you can either get too many of them, or maybe not the ones that you're after. Also, there are a lot of regression reports that are created automatically, and they not always point to real regressions. Because for a CI system, a regression is simply something that breaks a test. If a test goes from green to red, that's reported as a regression, but not all of them are caused by kernel changes. There could be infrastructure errors or hardware that failed for any reason, or the test could have had some changes that suddenly make it fail, and it's not a problem in the kernel, it's a problem in the test. There's another problem, which is the current CI systems provide only very basic structure and information about regression. So as I said, as long as a test that was running is now failing, that's reported as a regression. But the information that you get normally is just the version that introduced the failure, the kernel config, the kernel version, build information, etc. And it turns out there's a lot more things you can get out of that if you do the right work. And finally, there's this problem that I was talking about when I mentioned Rexbot. CI systems don't really model the life cycle of a regression. They consider a regression as a static thing, something that happened from one version to another. But regressions, as we'll see, are a living thing. They have a life cycle. And as far as I can tell, there are no CI system that's taking that into account and that's providing that kind of information. The closest that we have is Rexbot, which is tracking the life cycle of a regression, but that's separate from CI systems. You want to continue? Okay. So there are a few solutions that we think could work to mitigate these problems. And the first one would be to improve the quality of the regression data provided by CI systems. So right now, what we have in all of these systems is a bunch of primitive and basic data from a regression, which is which test is failing, what was the environment, how the kernel was built, what was the version that caused the failure, and the test log, the test output. And this is all developers are getting today in a regression report. But we figure out that if we take this same data and we do something with it, we post-process it, we can extract more useful information for developers. So, for example, if you could zoom out the results of a test, and instead of seeing a single failure, you can see the historic information about the test, and you can see that the test is actually, well, it didn't fail today. It was working yesterday, failing the day before. There's a bunch of inconsistent results that don't seem related to the kernel version. So it could be the test is unreliable because there is a race conditioning somewhere, because there is something failing in the whole chain from hardware to test definition and test run. So maybe this is not a regression, it's a false positive instead. Same way, you could find neighbor results from the whole cloud of data that you have in the database, and maybe discover that other tests running in the same lab setup around that time were failing, all of them. So maybe this is not a regression. It was a problem in that lab specifically, or in that setup. So you can filter this out. It doesn't look like a regression. It's a problem because, I don't know, a particular laptop in the lab failed, or because the lab was shut down for whatever reason. But this, again, this is something that you can extract from the base test results data. Same way, you can get results from the same test on the same kernel version, but with different kernel configs or different hardware boards or different combinations of things. You can change 1 degree of liberty and see how the results were. And this way you can narrow down the possible causes for the regression. Instead of giving the developer a simple test result, you could say to him, okay, or to her, this failed, but worked in this other hardware, or this is failing just in this laboratory, or this is failing only with this particular kernel configuration, but this other is working. So that way you can kind of do a first step towards helping the developers investigate the problem. And important thing as well is log analysis. We are getting a lot of log information from all the tests, but we are doing nothing with them. We are just presenting that to the developers and the maintainers. But if you could do some smart parsing or matching with different logs from different regressions, you could actually figure out maybe what it looks like. You can maybe do some type of classification of the regression based on the log, or you can find similar regressions based on the log as well. This is all in the air. What we did do during the past few months is to do some experiments based on kernel CI results with a proof of concept that we wrote that was basically trying to do a bunch of this to help us because we are trying to work on regressions, and we found out that it was quite hard sometimes to investigate some of them, and it was a wasted effort because a lot of times they weren't really kernel regressions. They were something else that was failing. So we wrote a bunch of scripts in a utility to help us do this kind of manual work more automatic and help us filter out a lot of things that weren't really interesting to us. So adding this extra layer of scripting, of post-processing, can help us filter out some things that aren't really interested, aren't really regressions, can perform some sort of automatic categorization of regressions. So for instance, well, the first layer of this would be just filtering out. So if a regression failure looks like an infrastructure error, then we can detect that from the log, and we can filter that out. It's not a regression, it's something else. So doing some log matching, we can maybe help create some categories and do some automatic classification of regressions, and help doing an initial pre-triaging stage for developers. There are a lot of people who are trying to do work with regressions, and the first step is always trying to figure out which ones are the most important to tackle first. So having a tool that help you do, maybe not automatically do the triaging for you, but helping you take a decision about the criticality of the regression and the impact could be really a time saver. Yeah.
And like for now, like it has been only experiment that we've been trying things out and see how it works. Looks like with some of the kernel CI data. But the place where we are looking at right now in terms of implementing a solution that will be like more permanent in the community is KCIDB, which is coming out of the kernel CI Linux Foundation project. And it's intending to collect data from different CI systems across the community. So there's like data that Red Hat sending there, Microsoft sending there, kernel CI sending data there, Sysbot sending data there. 0 Day, I think, is sending data there as well. So we have like this collection of data from different CI systems, different like testing systems, and then we can start like adding some intelligence on top of it. So that's kind of like the idea we are trying to is slowly making progress into it. So that's like that's the goal. We are here trying to make progress on it. Maybe we should open for discussions. Maybe people have things on their mind already. Yeah. We can do step by step, I guess. Like, yeah, that's because they're different solutions. Yeah.
I was curious if you can elaborate on the scope of the types of tests that you are interested in for finding regressions.
Well, I think from a community point of view, we are interested in pretty much like any test. But as a collaborator, as a consultancy, we are focusing like first and foremost on the test that our clients are interested in. So our main use case right now is like device testing, like the work that Nicholas just presented, for example. Like he's looking to how can we detect like the probe of like device testing. But the idea is to make this as generic as possible. Like, but right now we are starting from a place that we have like problems to solve.
Sorry, but ultimately the solutions that we are talking about should be applicable to any kind of regression. It's not tailored to any specific type of regressions. We're just playing around certain type of regressions because that's what we have at hand and what looks important to us. But nothing about this is specific to a particular type.
Are they all feature regressions though, or any of them performance regressions? Are they like benchmarks?
So far, we're only dealing with non-performance related, but yeah.
So do you envision in the long term this actually turning into something that you could be actively trying to automate the analysis of? So for instance, if you see you have a bunch of categories of things where maybe you can detect infrastructure problems, right? So a board goes down in the lab. You don't want to treat that as a regression. So would you ever see that cycling back into the testing infrastructure itself to say, okay, well, I see that this has failed on, well, going back to my one board, do I want to test the same thing on a different board? So, I mean, I guess how prescriptive do you see this becoming?
I don't think we have like any solution in mind yet, but those are problems that we have to solve as we see them. Like it's just like there is way too many problems in front of us right now, and we are trying to pick like some of those bottlenecks and make progress on that. Like so, cleaning up, filtering things, and so on. That's like I think the testing labs is one specific point, and if we look like to bigger cycles, we also want to go like how much can we do on a pre-merge scenario as well? Like, can we insert like more pre-merge data so we can feed that back and solve things from that point of view as well? Like that's maybe further down the line because there's just too many problems to solve.
You talked about.
Wait a second. I want to add something to that. That has actually happened at collaborating this feedback loop because now that we are able to detect some infrastructure errors, we can create some statistics about, hey, this kind of device is failing more than the others in the lab. Why is that? We can tell about that. We can tell the lab people about that so they can figure out what's going on and can find a solution. Until now, we just knew that some devices were failing, but we didn't have any actual concrete data about which ones and in which tests. So this is, again, a way to close the loop with the lab people.
You talked about contacting the right people on the right mailing lists. You should just tell them to use lay and everybody, like make some kind of searchable thing.
Yeah. We are going to that in the next slide.
So another thing is that you're also looking at two different things, right? Reporting regressions and then also providing as much information as you possibly can to maintainers and developers. So if a test fails, would it be something that you could trigger on a test failure and say after it fails, rerun the test with more tracing enabled? Is that something you're looking into? Gathering, so if you ran a test suite and some of the tests failed, so just run those tests on the same system, same board, with more FTS enabled or tracing enabled or events enabled, and gather more information that way. That might be very helpful too when you're reporting.
Definitely, like the driver for the work is like the community and maintainers. Like based on the use case that we have for our clients, like it's the maintainers and developers who are going to give the feedback. Like, hey, can I do tracing after that fails? Yeah, we can implement that. Yeah, because we want to solve the problems from the maintainer's point of view, not from the CI point of view.
Yeah, so anticipate what developers would need. I think Thorsten has, he just woke up. So he's saying he woke up. So he put together a list. He was talking about what would be beneficial. And as I'm thinking about it, there are a lot of things that would be beneficial. Of course, gathering T-message, which CIs tend to have that information. And then the other thing could be get more information after test fails. So that's the thought I had.
And I think the other thing is like each maintainer will require a different thing. So we need to make account for that somehow. Like in USB is one thing, in file systems a different thing.
Well, you can start with a common denominator and start
Mhm.
adding things,
Yeah.
of course.
Yeah, one other thing, and I suspect if you're going to continue talking about how to deliver regression reports, there are two sort of different axes on which audiences for these sit. There are the people writing the code that has caused the regression and the people who've written the test that's failed. And it's a different perspective, but important to sort of target both groups.
I just wanted to say, I mean, my background is more like KTAP. So, and you said log analysis, you feel like you could get more out of it. I'm wondering if we could encourage specified types of warnings or errors that could give more information to you all. That could be helpful. And then you could compare it over different runs, seeing which ones you're getting different types of errors or warnings. Would that be useful?
Yeah, definitely. That was one of the things we were talking about a few months ago, like having a common definition of test results all across the board, because right now it's a bit, I mean, every test is basically built differently and provides a different set of logs and results. And there's so much manual work to do to collect their results and go through them and investigate the problem. So yeah, that definitely would help. But it's, again, everything that we are presenting here is like too far-fetched in the future and needs so much collaboration. And basically, that's why we're here. This is our first step into probing the community to find out who is interested and who wants to cooperate in this kind of undertaking. So yeah.
Oh, wow. That's a
EY wants like since a while.
Thanks, Gustavo, for the presentation. One of the things is, I kind of run CKI at Red Hat, which is very similar to your service here. Is, sometimes tests fail; they can't always be reproduced. So bisecting is kind of out of the question, which kind of goes to Shua's point: is there ways to get more logs out of there? We've run into some resistance in the community about if our test fails and we can't bisect, that they're not interested in the results. But if we provide more log data, is there people in the community who'll be willing to sift through the log data to kind of try to mentally figure out where the problem is, as opposed to relying on a bisectable patch? I'm assuming you guys have seen similar.
Yeah, but bisecting is by far the best tool that there is for developers to investigate a regression, but it's not the only one. I mean, we have fixed regressions without bisections just by collecting this kind of data that we are talking about. It's not that it will fix, it's not that it will find the problem for you, but it will make it easier to find out where to look at. If you have this kind of, ways to filter out or to direct you to where the problem could be, and weed out all the parts that aren't probably a cause for the problem. I don't know if that answers your question.
So you're able to successfully bisect test results?
What do you mean with bisecting test results?
The test fails.
Yes.
So the first question developers ask is, what patch caused that test failure?
Yeah.
My experience is bisecting a failed test is hard because it's not always reproducible, which means you always go down the wrong path, or there's a good chance you go down the wrong path and lead to the wrong test.
Yeah.
Kernel CI can do some of that. Like not always it will find it, but it can find like oftentimes the commit that's failing the test. And then we have like hit checks and so on. And during this effort, we found out some of like regressions that were bisected, were verified by Kernel CI, but it was still wrong. So there's more work to do in there to figure out that, because what we don't want is start like reporting that as if it was like a true regression, and then you just burn the reputation of the maintainer, and then they stop looking to a report.
So based on some of I know we have a bunch of automated testing inside of Google, and at least one solution that can kind of work for the non-bisectable, non-reproducible things is to work on seeing if you can generate a signature of the failure somehow. So if you can somehow take that failure and generate some signature that's unique enough for that failure, then you can start looking at it across more test results. And so you may not be able to say it started with this particular commit, but you may be able to at least say, hey, we saw it starting on this date, or we saw it across a bunch of different boards, or essentially the more you can sort of gather a signature about the failure, the more information you can get about it. So maybe when you see it the first time, you don't send out any kind of regression report. But maybe if you say, start seeing the signature show up 1 out of every 200 tests, and the first time you saw it was, January 3rd, 2023, it's probably worth investigating because it's some sort of regression, right? Maybe at that point in time, you can start trying to do a statistical bypass or a bisect. But that would be what I would focus on, is looking for trying to generate a signature of the failure, which will help you correlate it among a bunch of runs.
I think
So
KY.
I've seen that happen a number of times, that some test fails randomly. And what I've done, I think my record was that I had to repeat the test like 200 times to get a reliable signature. And then, of course, you don't run a bisect like this, it runs over days. Quite some success this way. It takes forever to run those bisects if you can identify what actually introduced it or when it was introduced. If you see like, it was introduced with 6.1 or after 6.1, if you at that point, and then it's like, okay, you run like 50 rounds of bisect and repeat each step 100 times, you can find it. But yeah, it does take forever.
Yeah, stress test goes a long way usually to reproduce those flaky tests. And I think to your point, like if you can isolate when it started failing, you actually go a long way also, because it's probably not, you don't know exactly which patch failed and make it fail, but you can find when it started. And usually like having time series over time where it's like green and then all of a sudden it starts flaking red, it's a good help to find and isolate. But my understanding is from your system, it's actually out of band, right? So it gets, in this case, you want to be able to feed in the result from their system into your CI to be able to say, I should start, rerunning the test and stuff like that.
Yeah. My struggle is I just don't have I have a CI system that finds the thing. I just don't have the manpower to bisect it or, analyze it like you guys are talking about. It's unfortunate. I'm looking for more.
Okay. Can you have KUI? He has been waiting for a while there.
All right.
Yeah. Finally.
A couple of questions. I love the idea of generating a unique signature for these regressions. Maybe we can talk about what format, what are the things that should go into the signature, right? That would be super useful to be able to tag something uniquely forever, right? That's one thing. The question I really wanted to ask is, very often I'm not interested in all the regressions. I'm interested in regressions I might have caused, checking in some new code, right? So to the extent we can filter out known issues and only look at new issues that have come up, right? That's going to be super useful as a PR gate. As we try to look at, what should we do to make sure that we haven't regressed in quality from where we were. We always have bugs, that we know that. And so how do we manage the incremental, change in quality that has occurred? All right.
Yeah. So one of the things which might be really useful is I think many of us actually have automatic rebasing systems because Git rebases like the core, right? And that sort of works everywhere. But what you need is something that can iterate a test. I've seen some people need to do it 500 times. And very often, if it ends with the system crashing, it ends up being very, very specific to your CI system because you're actually having to grab the serial console output and then analyzing the serial console output to find the kernel oops message. And then sometimes the signature is not exclusive. Like, for example, if it's a lockdep warning, which Sysbot really loves to give us, there will be like 3 different lock depth warnings depending on which order you hit things, where they will say that, you know, the bug is a deadlock on this lock, or lock B, or lock C. And it's really all the same bug, but the system isn't smart enough to figure that out. So one of the things that I would really love is if someone would like to come up with some sort of automated crash signature analysis, right? Python module that will like grab the serial console output and uniquify it. Because the other thing that gets really annoying is many of these automated bisect systems will assume that any crash is the same signature. And so I end up getting like an HR timer bug because it bisected to that, even though the bug was somewhere else, because there were multiple crashes that, you know, caused the bisection to go awry. So the whole finding a good crash signature is a key insight. Doing that well is hard. And to the extent that that could be an interchangeable module that we could all plug into our own CI bisecting systems, I think would really sort of help the system. The other thing I'll note is if you're having to run the test 200, 500 times just to find the darn flake, the pro tip is the first time it fails, it's a bisect bad, right? And that's one of the other things that a lot of these systems don't know how to do is they insist on running the test 200 times, even though the first time you find a bad failure, as long as you can be reliable that the failure signature is in fact the right one, you don't have to run it the other 450 times. So.
Yeah, and I think like looking to crash reports, analyzing them, it's like it's maybe one of the biggest path for prioritization of the issues, because then you can tell me like, oh, I've been seeing like this 1,000 times in my internal systems, and then you can inform the community of that, and that becomes a higher priority.
Thank you so much. Thanks, everybody. Thank you.
Oh yeah, one more thing. We have a BOF about this on Thursday, so we can continue the conversation. Yeah,
That's
and
awesome.
Thorsten will be with us there. From yeah.
Awesome. Thank
Thank
you very
you.
much.
Yeah.